From Earth, Orion's belt looks like a blur, but below it lies one of the most dangerous and beautiful places in the known universe. It's not just a cloud of gas. The Orion Nebula is a cosmic furnace where stars are born in fire, shaped by gravity, and bathed in radiation. It's chaos and creation going on right now, only 1,300 light-years away from Earth. If you could see it with infrared eyes, you would see the universe giving birth over and over again inside a cloud that shines with the secrets of the sun's past. Where exactly is the Orion Nebula, and how far away is it? You can see Orion in the winter sky. It looks like a hunter with his sword raised and his belt shining. Under that belt, if it's dark enough, you might see a small fuzzy piece hanging from the sword. It's not a star patch, it opens up. The Orion Nebula, which is also written as Messier 42 or M42, is a bright womb of gas and dust between the stars. People have studied, recorded, and made up stories about this part of the Milky Way more than any other. But where is it exactly, and how far do we have to go in terms of ideas or technology to get there? The Orion Nebula is located in the Orion Molecular Cloud Complex, a massive stellar nursery that spans hundreds of light-years. This cloud complex includes other well-known structures like Barnard's Loop, the Horsehead Nebula, and the Flame Nebula, all stitched into the fabric of Orion's sword. M42 is the brightest part of this giant structure, visible even without a telescope, though only as a misty blur. It lies in the direction of the Orion Arm, a minor spiral arm of the Milky Way where our own solar system resides. That means the nebula isn't just out there somewhere in the cosmos, it's in our neighborhood, cosmically speaking. How far away is it really? For many years, people disagreed about how far away the Orion Nebula was. It was thought to be between 1,500 and over 1,800 light-years away at first. But as we got better at using our tools, we got closer to the goal. With the most recent data, the Orion Nebula is now thought to be about 1,344 light-years away, give or take a few. If you want to be exact, that's about 7.9 quadrillion miles, or 12.7 quadrillion kilometers. These numbers aren't just guesses. They come from measures of parallax and radio interferometry. This is how it works. Close one eye, then the other, and watch an object close up, seem to move. This is the same idea behind parallax. The same thing is done by astronomers with telescopes 6 months apart on opposite sides of Earth's orbit. They figure out how far away the nebula is by measuring how much certain stars in it seem to move compared to stars in the background. It's simple math on a very large scale, but parallax can only help you so much. Very long baseline interferometry, VLBI, is a method that mixes data from several radio telescopes located around the Earth to make it look like one big dish. It works well for studying something as big and spread out as a nebula. Scientists have cut the mistake to less than 20 light-years by using VLBI and space-based telescopes like Gaia. When it comes to the cosmic scale, that's very close. Things are getting even stranger now. The Orion Nebula isn't just a flat spot in space. It has depth. It has stars that are tens of light-years away from us and stars that are far away. You can see layers, like when you look into a foggy forest. Some of the outer molecular clouds are farther away than the Trapezium Cluster, which is the bright center of the nebula. We're really looking through a region of space instead of at a single distance, and that volume is alive. The Orion Nebula is massive, about 24 light-years across, give or take, but it's just a sliver of the full Orion Molecular Cloud Complex, which stretches nearly 240 light-years in length. What we see glowing in visible light is just the thin, ionized skin of a much deeper structure, lit up like a paper lantern from the inside. Being this close and this active, M42 has become a benchmark object, a kind of galactic Rosetta Stone. It's one of the few places where we can study nearly all phases of stellar birth, from cold gas collapsing under gravity to fiery newborn stars burning away their surroundings. And because it's nearby, our instruments can resolve details at much finer scales than in more distant nebulae. Want to study planetary systems in the making? Orion's got them. Curious about how radiation sculpts cosmic matter? It's all there, happening live. Distance does matter when it comes to time, though. What we see tonight is light from the Orion Nebula that left around the year 681 AD. That means we're looking at a nebula from the 7th century. Back then, when Earth's societies were rising and falling, this light was just starting its trip. We wouldn't know for another 1,300 years if the trapezium stars went supernova tomorrow. What makes the Orion Nebula glow? Ionization behind the light. Things in the Orion Nebula look like they are on fire. Deep reds, fiery blues and eerie greens. It looked like an oil picture of space was thrown across the sky. These colors aren't just pretty though, they leave a chemical mark, a word that is written in light. What then is making all this light shine? Why does Orion shine like a lighthouse at night while most molecular clouds stay dark and out of sight? The answer comes down to ionization, a raw, powerful process triggered by young, massive stars. At the heart of the nebula lies the Trapezium Cluster, a group of young stars that have just ignited nuclear fusion in their cores. The brightest and most influential of them all, Theta 1 Orionis C. This star is a monster, dozens of times more massive than our Sun and thousands of times more luminous. It emits an unrelenting torrent of ultraviolet radiation that floods the surrounding gas. The Orion Nebula is filled with hydrogen gas, the simplest and most abundant element in the universe. When ultraviolet photons from stars like Theta 1 Orionis C slam into hydrogen atoms, they knock electrons completely off. This turns neutral hydrogen, H, into ionized hydrogen, H2. It's a violent process. Think of it as atomic-level lightning. These free electrons don't stay separated forever. They eventually find their way back to the positively charged protons. And when they do, they release photons, light, at very specific wavelengths. These emitted photons form the glowing spectrum we see from the nebula. This is recombination radiation, and it's responsible for the iconic pinkish-red color that dominates images of Orion. Specifically, the most common line observed is called H-alpha, a deep red emission at 656.3 nanometers. There are other parts of the nebula that are caught in this light storm as well. For example, oxygen is energized twice and glows a hazy greenish blue. Sulfur makes the color of red darker. Each color stands for a different element and energy level. Then, scientists don't just enjoy a light show when they look at the Orion Nebula through different screens. They're reading about its chemicals in real time. The nebula doesn't glow evenly. The areas that are closest to the Trapezium Cluster shine the brightest. That's where the ultraviolet bombardment is most intense. As you move outward, the radiation softens, and the gas transitions back to being mostly neutral. This creates a kind of layered effect, a radiation gradient where the inner regions are ionized and hot, and the outer ones are cooler and darker. This boundary between hot ionized gas and cooler, neutral gas is known as an ionization front. It's not a static wall. It moves, erodes, and reshapes the nebula over time. The intense radiation pressure from the central stars is actually blowing away the outer layers of the gas cloud, revealing the denser star-forming regions hidden beneath. In effect, the light of Orion is both the storyteller and the sculptor of its shape. The fact that we can watch this process happen is very interesting. Parts of the Orion Nebula have changed in a way that can be seen in just a few decades, while galaxies and faraway quasars change over millions of years. Time-lapse pictures taken by observatories like the Hubble Space Telescope show how gas knots move, shock fronts spread, and ionization edges change shape over spans that humans can understand. This light is also dangerous. The ultraviolet light that makes the nebula shine can also be bad for making planets. It uses light to clear gas rings around new stars, getting rid of the stuff that could become planets. This back and forth between making things and destroying them is part of what makes the Orion Nebula so interesting. The light we admire is also what risks the futures of the systems that are just starting to form. The Orion Nebula's glow is not actually very bright in real life. Our eyes can't see most of it clearly, especially the red hydrogen emissions. most of those stunning colors you see in telescope images. They're captured using long exposures and color filters. That doesn't make them fake, they're scientifically accurate translations. They reveal light our eyes were never evolved to see. If we could tune our vision to match a high-powered camera, we'd see the nebula like a stained glass cathedral lit from within. The Trapezium Cluster, a stellar engine room. If you think of the Orion Nebula as a womb, the Trapezium Cluster is its beating heart. In the middle of the nebula, close together, there is a group of huge new stars that have such an impact on everything you see and a lot of things you don't. Their heat, light, and radiation are what's making the chaos happen. There would be no Orion without the Trapezium Cluster. It would just be a cold, dark cloud. Instead, it's a heater in space that was built from the inside out. The cluster gets its name from its 4 brightest stars, which form a rough trapezoidal shape when seen from Earth: Theta 1 Orionis A, B, C, and D. These stars are only a few million years old, infants in cosmic terms, but their youth doesn't mean weakness. Quite the opposite. These are O-type and early B-type stars, the most massive and energetic classes known. Their surface temperatures can exceed 40,000 Kelvin, making them searing blue-white beacons in the sky. The most important of them all is Theta 1 Orionis C. This single star is responsible for nearly 90% of the ultraviolet radiation that ionizes the gas in the nebula. It's not just big, it's monstrously powerful. Its stellar wind, a constant outflow of charged particles, blasts through the surrounding gas at speeds of 2,000 kilometers per second. That wind carves out cavities, sculpts walls of glowing material, and triggers shock waves that ripple through the surrounding cloud like detonations. There are hundreds of stars in the Trapezium Cluster, not just 4. The cluster is made up of more than 700 young stars, some of which can be seen with visible light, and some only in infrared light. Their sizes, ages, and activities are all very different. Some are still ringed by rings of dust, which could be early stages of solar systems. Others are already erupting with strong jets and magnetic storms. They make up one of the densest groups of stars ever seen in the Milky Way. What's crazy is how unsteady the whole thing is in terms of gravity. The trapezium stars are all crowded into an area that is only 1.5 light-years across. That's smaller than the distance between our Sun and Alpha Centauri, the nearest star system. Because they are so close, their gravity fields are always pulling on each other, changing paths and sometimes shooting smaller stars out like slingshots. Some stars in the Orion Nebula may be runaways, which means they were thrown out from the center by interacting with these big objects. This chaotic interaction doesn't just affect stars, it shapes the nebula itself. The intense radiation from the trapezium blows bubbles into the surrounding gas, creating cavities and tunnels that allow ultraviolet light to escape in focused directions. These directional blasts can carve pillars, create bright rims, and even trigger new star formation when they compress nearby gas clouds. It's the ultimate feedback loop, stars shaping the environment that makes more stars. It's also interesting to see how the trapezium cluster affects mass segregation, which is when the heavier stars move toward the middle of a cluster over time. In the trapezium, on the other hand, it looks like it happened pretty quickly. It's still not clear whether that's because of how gravity waves changed after the cluster formed, or because of how the cluster itself formed. But the result is clear. The biggest and brightest stars are squished together in the middle, ruling over this stellar nursery as well as giving birth to new stars. The protostellar rings, also called Proplids, that circle some of the stars in and around the trapezium, are even more interesting. They are the building blocks of future solar systems, and the trapezium's radiation is forming, wearing away, and sometimes going through them. You can see teardrop-shaped shadows following these disks in high-resolution pictures. These shadows look like cosmic capes caught in the solar wind. There is beauty and violence at the same time. The trapezium cluster is a place to do research, a squished image of what it looks like when stars try to form too quickly and too close to each other in harsh conditions. Every spark, wave, or IR flash is a new piece of information. Another hint at how our sun may have come to be. In chaos, among giants, in the light of something much bigger than itself. Don't start with the Orion Nebula's colors if you want to understand it. To begin, look at the trapezium. That's the brain, the heater, or the beast that's making all the noise. Proplids, the solar systems in the making. They look like ink drops moving through the air, little shadows with fire around the edges. These things, which float near the Trapezium Cluster, are called Proplids, which is short for protoplanetary disks. These are solar systems that are still in the womb, and we can see them coming together in the Orion Nebula, not in general, not in the game, but in real time, caught by cameras that are sharp enough to cut through dust and light from stars. Each Proplid is a young star, often less than 1 million years old, wrapped in a rotating disk of gas and dust. It's a cosmic nursery, surrounded by the raw materials of creation: hydrogen, helium, carbon compounds, ice, silicates. Over time, if the disk survives long enough, particles within it can begin to stick together. First grains, then pebbles, then mountain-sized planetesimals. Eventually, they can become full-fledged planets, orbiting a star like ours. That is, however, the perfect story. In Orion, things are much worse than they seem, because these Proplids aren't just appearing out of nowhere in space. They are forming in the Trapezium Cluster's blast zone, which is constantly hit by UV light from big stars like Theta 1 Orionis C. The radiation turns the disks into vacuums, which removes the gas, heats it to thousands of degrees, and blows it off into space in long, following flows. A lot of the Proplids in Orion have tails that look like comets. This is because radiation is literally peeling back the outer disk and turning it into vapor. This makes Orion both a birthplace and a battlefield. These young planetary systems are racing against time, trying to collapse dust into planets before their raw materials are destroyed by the very stars lighting up the nebula. It's the cosmic equivalent of trying to build a house during a sandstorm, with a flamethrower aimed at your blueprints. Still, life finds a way. Even though it was destroyed, dozens or even hundreds of Proplids have been found in Orion. Some are tight and thick, with plates that aren't worn down much. Others are already getting thinner, leaving less stuff that could be used to make worlds. Their ability to stay alive seems to depend on how close they are to the trapezium. The radiation gets stronger as they get closer, which shortens their lives. Some Proplids are surrounded by Bowshocks, arc-shaped structures formed when the stellar wind from the central star slams into the surrounding ionized gas. These shocks mark the boundaries of stellar influence. They also hint at just how much energy is being thrown around in this nursery. It's like watching 1,000 hurricanes interact, each with their own gravity, spin, and heat. Thanks to Hubble and more recently JWST, we've been able to peer deeper into these disks than ever before. In some, we've observed gaps and rings, possible early signs of planet formation. These features echo what we see in older disks, like those around stars in the Taurus region, or in the famous HL Tauri image. Orion offers a younger, more chaotic version, a look at what may have happened before systems like our own even settled into structure. And these hypotheses aren't just nice to look at. They're hints about how we got here. Our solar system may have begun in a place like this, where it was bathed in radiation, formed close to huge stars, and struggled to keep its protoplanetary disk whole. There's even proof that supernova debris may have been sucked into our early solar nebula. This means that, like them, we were born in a chaotic, clumped world. It's not just fun to look at the future of other systems when we study Orion's Proplids. They help us figure out our own past. Another intriguing possibility: some of these Proplids won't make planets at all. If they lose too much material too quickly, they may collapse into brown dwarfs or low-mass stars, a different evolutionary path, still shaped by the violence around them. Others might birth rogue planets, worlds ejected from their systems during gravitational interactions, doomed to drift the galaxy without a sun. Each bright bead in Orion has its own story to tell. Some are putting up, a few are breaking. Some may already have huge worlds like Jupiter forming deep inside their dusty rings. We don't know what each will become, but we can watch the fight. One of the most amazing things about modern astronomy is that it lets us see how planetary systems are put together as they are first being formed. Brown dwarfs in Orion, failed stars or cosmic fillers. There are a lot of things in the Orion Nebula, and not all of them can be called stars. Some people try, some almost make it, but some fall just short of becoming stars because they can't start the nuclear fusion that makes a star. Brown dwarfs are these kinds of stars, and Orion is full of them. Brown dwarfs are sometimes called failed stars, but that nickname doesn't do justice to their weirdness. They're not quite stars because they don't have enough mass, typically less than 0.08 solar masses, to sustain the hydrogen fusion that powers the Sun and other main sequence stars. But they're also not planets, since they form the same way stars do, by gravitational collapse of gas in a nebula. That puts them in a strange identity crisis, too big to be a planet, too small to shine like a star. In the Orion Nebula, brown dwarfs are surprisingly common. Thanks to infrared surveys and high-resolution imaging from telescopes like Hubble, Spitzer, and now JWST, astronomers have identified dozens, maybe even hundreds of these objects hidden within the dusty folds of M42. They're often lurking near more massive protostars, like little siblings in the background, easy to overlook without the right tools. Many of these brown dwarfs are very young, maybe only a few million years old. This makes Orion one of the best places to study how they formed and how they have changed over time. The brown dwarfs in Orion are still warm from being formed, unlike the older ones that float around the galaxy. Like real stars, some of them have rings of dust around them. This makes it possible that brown dwarfs could have their own planetary systems, though they would be smaller and cooler. But how do they come together? That's where things get unclear. One idea is that brown dwarfs are made the same way stars are, from gas clouds that collapse but never get heavy enough. Another idea is that they were once part of bigger systems that were forming, but were thrown out by gravitational forces, like a loser being thrown out of a busy theater. This would explain why some brown dwarfs appear to be alone and others stay close to groups. In the Orion Nebula, we see evidence of both scenarios. Some brown dwarfs are embedded in the densest parts of the cloud, surrounded by gas and possibly still accreting material. Others are drifting solo, far from the action, as if they were flung out during a cosmic scuffle. The chaotic gravitational soup of the Trapezium Cluster could easily toss a low-mass object across light years. Some objects in Orion have masses below the brown dwarf threshold, as low as a few Jupiter masses, yet show evidence of having disks and possibly forming moons or microplanets. These objects challenge our definitions entirely. Are they rogue planets, sub-brown dwarfs, planetary embryos without a parent star? Whatever they are, they don't fit neatly into any category. Orion is a breeding ground for rule breakers. Being able to see brown dwarfs is hard because they don't give off much visible light. The best way to see them is in the infrared, where their heat glows slightly. Some of them even send out flares and X-rays, which shows that their magnetic activity can be like that of bigger stars. They're not just gas balls that don't move. They're live things that are moving and changing on the edges of star physics. And though they may be dim, brown dwarfs may be numerically dominant in regions like Orion. That's right. There may be more brown dwarfs than stars in some star-forming regions. They don't contribute as much light or heat, but they count, mass-wise. They fill in the spaces. They shape the gravitational environment. They are the quiet majority. So why do they matter? Because brown dwarfs blur the line between planet and star. And that makes them crucial to our understanding of how everything forms. Are they an accident or a natural byproduct of clustered star formation? Do all nebulae produce them, or is Orion unusually rich? And if these substellar objects can host planets or moons, could they, quietly, unnoticed, harbor life in dark frozen systems? It's not easy for Orion to reveal its secrets. But every brown dwarf we find, and every infrared glow in the dark, is a new clue. This is another piece of the range of what can happen when gas falls apart under its own weight. Not every cloud turns into a sun. Being nothing doesn't mean becoming a sun, though. Turbulence in the nebula, the chaotic cradle of stars. Stars don't form slowly. It's rough, unpredictable, and hard to keep under control in the Orion Nebula. Do not think of the beautiful pictures of stars slowly growing in the dark. This place is more like a riot. Light, wind, gravity, electricity, and shock all at once. The galaxy is moving all the way through, and that move? It's not noise in the background. It's an important part of how stars are made. The Orion Nebula is a textbook example of turbulent star formation, where supersonic flows of gas smash into each other, collapse under gravity, and twist in spirals around embryonic stars. These flows are not calm streams. They're shock waves, jet streams, and magnetic cyclones, each one moving at speeds of tens to hundreds of kilometers per second. You're looking at an interstellar tempest, something between a hurricane and a detonation, unfolding across dozens of light years. Where does all this chaos come from? It all starts with weight. As thick areas of molecular gas start to fall apart from their own weight, they pull in more matter, speeding up the falling. But this gas that is falling doesn't just fall in softly. It slams, crashes, and breaks up. As the core forms, the pieces twist and turn around it. In a smooth, idealized universe, this would all happen neatly. However, Orion is not perfect. It's a mess. The gas coming in comes from many places, and it hits and squeezes things in different ways. Besides that, there are the stellar winds that come from big stars like those in the Trapezium Cluster. These winds are bursts of charged particles that speed through the nebula faster than sound, adding motion and making holes in it. They cause chaos everywhere they go, like jet engines tearing through a fog bank. As a result, shear zones, eddies, and clumpy structures are places where gas builds up and then falls back down quickly. And it's not just physical motion. There's a whole layer of magnetism interwoven in the chaos. The Orion Nebula is threaded with magnetic fields, invisible but powerful. These fields resist the collapse of gas, slow down some flows, and channel others along specific directions. They act like unseen scaffolding or cosmic tension wires. But under pressure, even magnetic fields can buckle, adding one more layer of stress to an already explosive environment. This is why Orion's star formation is both efficient and chaotic. On the one hand, you have these collapsing cores rapidly forming stars, some in as little as 100,000 years, an eye blink in cosmic time. On the other hand, you have material being blasted apart, evaporated, and jostled out of equilibrium. It's a feedback loop of destruction and creation. Every shock front can trigger a new collapse, or disperse a potential star entirely. Astronomers study this wind flow with both pictures and spectroscopy. They can make a map of the speed of gas by looking at how light moves from different parts of the nebula. They find something crazy. The speeds vary a lot from one area to the next. Some gas is moving away from us and some is moving toward us. Some of it gets stuck in tight twists and some in long straight-line flows. The nebula as a whole is a three-dimensional jumble of motion with speeds that don't go anywhere. And yet, patterns emerge. In the densest regions of turbulence, you'll often find the youngest stars. Why? Because those are the places where chaotic pressure builds up and forces collapse. It's like twisting a balloon until a bulge forms. Eventually, it has to give. These pressure points create dense clumps that rapidly form protostars. In a way, turbulence is both the antagonist and the matchmaker. It prevents easy collapse, but when it does allow it, the result is explosive. This is the reason why stars don't form evenly across the Orion cloud. Instead, they form in groups, patches and strands in places where the turbulent flow came together just right. It is likely that some stars form in strings that follow shock fronts or magnetic waveguides. Though it's wild, it's not random. Understanding this chaos isn't just for school. It has effects on everything, from how big stars form to whether planets can form afterward. The gas might never settle into rings if there is too much disturbance. If it's not strong enough, the cloud might fall apart too slowly to keep up with the strong radiation from close stars. It's not just heat or mass that make up the Goldilocks zone for star creation. It's also managed chaos. We see that confusion in high clarity in Orion, wisps of light that look like art. Those are strands of shocked gas moving faster than sound, shapes that look like arcs and ripples. They blast waves from new stars or flows that are combining. It's not just gas. Stars are the ones who made it off the fight alive. Mass segregation, why the biggest stars cluster at the center. There is a strange event going on in the center of the Orion Nebula. The biggest stars in the Trapezium Cluster are not spread out in a random way. All of them are huddled together in the middle, like important people in the middle of a storm. There are hundreds of tiny stars, brown dwarfs, and disks that are making planets all around them. It's not an accident. The event in space is called mass segregation, and it can be seen very clearly in Orion. But wait a minute, what does mass segregation really mean? Mass segregation is the process by which heavier stars tend to move toward the center of a star cluster over time, while smaller stars are pushed away. This can happen because of gravitational interactions, which are kind of like billiards in space. Stars that are heavy and moving slower naturally settle into the gravitational well, while stars that are lighter and moving faster drift to the edges. It's kind of like shaking a jar with sand and rocks in it. The big stuff ends up in the middle after a while. In the Orion Nebula, that settling appears to have happened very early, perhaps even before the cluster was fully formed. In fact, some astronomers believe the mass segregation we see in Orion today is primordial, meaning the massive stars were born near the center. They didn't migrate there. They emerged right in the middle of the action. Why does this matter? Because it changes the rules of how we think star clusters evolve. If mass segregation is built in from the beginning, it suggests that massive stars only form under very specific central conditions, like the deepest wells of gravitational potential. It means the center of a collapsing gas cloud may be pre-programmed to give birth to giants. And what giants they are. Theta 1 Orionis C, the dominant star of the Trapezium Cluster, is about 40 times the mass of the Sun and emits thousands of times more energy. Its presence, and the presence of other massive O and B-type stars nearby, completely reshapes the environment around them. They generate ultraviolet radiation, strong stellar winds, and magnetic chaos. In doing so, they both fuel and suppress further star formation. Because they form first and sink deeper into the gravity well, the stars that are most likely to destroy their surroundings by blowing away gas, messing up disks, and heating the area are also the ones that are most likely to form. We can see how this input works in Orion. The cloud is flattened out, electrified and broken around the trapezium. The scars are caused by the radiation pressure of the giants in the middle. But why does division happen in the first place? One idea is based on dynamics alone. As the cluster grows and the stars interact, the heavier ones lose speed and naturally move closer together, like balls falling into a gravitational pool. There is a chance, though, that Orion, which is only 1 to 2 million years old, may not have had enough time for this process to finish. That's why a lot of people think that the nebula's starting conditions pushed most of its mass to the center when it was forming. Another idea is tied to competitive accretion. In this model, protostars in dense central regions of a collapsing gas cloud have more access to infalling material. They get bigger, faster, feeding from the environment like cosmic parasites with front row seats at the buffet. The stars on the edge? Less material, slower growth. This natural imbalance results in the massive stars forming first, in the core, and locking in their dominance. Their gravity can disrupt nearby stars, send them into elongated orbits, or even eject smaller objects entirely, turning them into runaway stars or isolated brown dwarfs. In this way, the mass segregation of Orion isn't just a static arrangement. It's a dynamic, evolving system where the center holds power and the edges feel the consequences. This grouping of things has real effects. It changes how long the nebula lasts, because big stars die young and quickly, usually in supernovae that can split the area in two. Radiation from center stars can photo-evaporate protoplanetary disks, which changes how planets are formed. It also changes the form of the cloud as a whole because gravity and feedback make holes, strands, and radiation walls. filaments and pillars, sculptures carved by radiation. The Orion Nebula is not a smooth blanket of clouds. The canvas is rough, with a web of curves, vines, and tall peaks that look like they were carved by hand. They are, in a way. There is a pattern to these strands and poles. They were made by star radiation, which is one of the most violent artists in the world. Ultraviolet light from new stars doesn't just light up Orion, it cuts it up. The nebula is made of gas and dust, but that material isn't evenly distributed. Gravity naturally causes some areas to clump, creating denser pockets of material. But once massive stars like those in the Trapezium Cluster form, they flood their surroundings with ultraviolet radiation. That radiation erodes the nebula, blasting away the lower density gas while leaving behind the denser chunks. Over time, these chunks become the pillars, ridges, and fingers of gas we see glowing in telescope images. This is called photoevaporation, a process where radiation heats the surface of a dense gas clump, causing it to boil off into space. The result is surreal. Towering columns of dense gas trailing away from the radiation source, each one outlined by glowing edges where the gas is ionized. These structures can be light years long, yet only exist because they are slowly being destroyed. Orion is full of these features. Some are large and dramatic, standing like statues in a cathedral of light. Others are thin and serpentine, filaments of gas twisted like ropes or spread like spider webs across the cloud. These filaments often connect multiple stars, as if tracing out the pathways of collapse and formation. In some cases, they're thought to channel material toward growing protostars, acting like interstellar arteries feeding embryonic suns. And at the tips of these pillars, you often find something remarkable: bright points of light, protostars, emerging from their dusty cocoons. These are stars being born at the edges, in the very places where radiation is eating away the cloud. It's a cosmic paradox. The destructive force of radiation is also what triggers new star formation by compressing the dense tips of these pillars until they collapse under their own weight. One of the most iconic examples in Orion is the structure known as the Orion Fingers. These are a series of narrow, linear jets and filaments shooting outward from a chaotic explosion near the Trapezium Cluster. Thought to be the result of a stellar encounter or merger, the fingers stretch across several light years and show just how dynamic this environment can be. It's not just sculpted, it's explosive art. The orientation of these pillars also tells a story. Most of them point back to the trapezium stars, like grass bent by the wind. That alignment is a dead giveaway. The massive stars at the nebula's core are driving the entire structure. Every curve, every edge, every flicker of light is a response to their radiation. These stars are like invisible chisels, constantly reshaping the gas with light alone. High-resolution imaging from Hubble and JWST has taken this to another level. We now see shadowed filaments where light is blocked by dust clumps, creating narrow dark trails behind them. We see photoionization fronts, the exact borders where ultraviolet light meets neutral gas. In some cases, we even see ripples, shock waves frozen mid-collapse, like sound waves turned to stone. Every detail is a freeze frame from a process unfolding over hundreds of thousands of years. There's something else in these strands as well, the start of new stars. A lot of these buildings aren't just scraps, they're full of possibilities. Right now, dense knots of gas inside filaments may be breaking into future stars. These stars can't be seen with the human eye, but they glow in infrared light. In fact, some scientists say that filamentary structure is a trait of all star formation, that stars don't form by themselves, but rather in networks of gas that are stretched thin by radiation and gravity. It's not just pretty, what it does. These curves show where stars are born, how long gas stays alive, and whether planets will form later. The difference between a clump that is falling apart and a puff of dust that is being worn away could be the difference between a new solar system and a blank sky. So when we see Orion's pillars and filaments, we're looking at more than decoration. We're witnessing the conflict between radiation and matter, the battle between what is being born and what is being erased. And the scars that radiation leaves behind, they're magnificent. The Orion Bar, a sharp boundary of ionization. The fight between stars and matter in most of the Orion Nebula is a mess. Pillars form, gas rips, and chaos rules. In one area, though, the front line is eerily clean. The battle between ultraviolet light and cold molecular gas has stopped in this place. It's called the Orion Bar, and it's one of the most studied points in the study of space. A place in space where light and matter meet directly. Visually, the Orion Bar is a knife edge of brightness slicing across the nebula, glowing like a golden arc beneath the Trapezium Cluster. But it's not a physical object, it's an ionization front. On one side, you have fully ionized hydrogen gas, lit up by intense ultraviolet radiation from the trapezium stars. On the other side, you have cold, neutral molecular gas, dense and dusty, shielded from the blast. And right in between is the bar itself, a razor-thin region where that UV light is absorbed, atoms get excited, and everything glows. Picture it as a cross-section of destruction in space. The Orion Bar gives us a very clear picture of how starlight cuts through a cloud. We have the best picture of what scientists call a photodissociation region, or PDR. Heavy photons break up molecules in these areas, but they don't fully ionize them like they do in the hot H2 areas. The Orion Bar shows the whole range, from hydrogen that is fully charged to warm gas that is only partially charged to cold material that is not charged at all. This isn't just pretty, it's also very useful. We can see the change in more than one way because the bar is almost on top of us. It's like cutting a cake open and seeing each layer. Astronomers use this setup to look at how temperature, density, and the makeup of chemicals change over space that is only a few trillion kilometers wide. Scientists can study the Orion Bar in more detail than any other area by using spectrometers on ground-based telescopes like the Very Large Telescope, VLT, and space instruments like Spitzer and JWST. One of the most important things these studies showed was it's hard to believe that the bar is only 0.1 light-years wide, which is about 630 billion miles. Hydrogen atoms lose their electrons in this small area, carbon ionizes, molecular hydrogen shreds, and dust grains heat up and give off infrared light. This is a very rough area where light and dark meet, like a cosmic skin. The Orion Bar also helps us understand the role of dust in shielding. Tiny particles of silicates and carbon absorb UV light, protecting the gas behind them from photodissociation. The density of this dust determines how deeply radiation can penetrate and how far into the cloud star formation can continue. If the shielding fails, the cloud erodes. If it holds, stars can form safely in the shadows. And here's where things get really wild. Shock waves from stellar winds often slam into the bar, compressing the gas even further. These shocks may trigger new star formation as pressure builds and clumps collapse. So not only is the Orion Bar a record of destruction, it might also be a cradle, nurturing the next generation of stars just behind the front line. When it comes to chemistry, the bar is a gem. It has a lot of spectral fingerprints like carbon monoxide, sulfur ions, oxygen atoms, and PAHs, polycyclic aromatic hydrocarbons, which all glow when exposed to radiation. Scientists can figure out what the gas is made of at the molecular level and follow how chemicals change as starlight changes the shape of matter. It's like seeing magic happen on a huge scale. The Orion Bar isn't static. It shifts over time as the trapezium stars continue to blaze and push the ionization front deeper into the cloud. If you could speed up time, you'd watch the bar crawl slowly inward, devouring gas layer by layer. In a few 100,000 years, the bar may be gone, its fuel spent, its stars formed, its dust blown away. But it's still one of the clearest lines of separation in the sky right now. Not just between states of gases, but also between ideas and the real world. At the Orion Bar, scientists try equations and match up simulations with real data to make their models of how light and matter interact better. It gets in the way. It's a window. You should be careful because radiation wins here. Magnetic fields in Orion, the invisible architects. The shape of the Orion Nebula is being shaped by a force that doesn't shine, flash, or roar. It doesn't break down gas like ultraviolet light does, or blast particles around like star winds do. The nebula wouldn't look the way it does without it, though. It could be fake or not around at all. We're talking about magnetic fields, which build the universe in a quiet, unseen way. While magnetic fields don't get flashy headlines like black holes or supernovae, they are absolutely fundamental to star formation. And in a chaotic place like Orion, where gravity, turbulence, and radiation are constantly colliding, magnetic fields are the referees, guiding, slowing, resisting, and redirecting the chaos. How do we know they're there? Even though we can't see magnetic fields directly, there are smart ways to tell when they are at work. One way is to look at light that has been polarized. Light is polarized when it goes through or bounces off of long dust grains that are lined up with magnetic fields. This means that the light's electric field starts to shift in a certain direction. To map magnetic field lines, instruments such as SOFIA, the Stratospheric Observatory for Infrared Astronomy, and ALMA, the Atacama Large Millimeter Submillimeter Array, measure this polarization. It's like using iron filings to trace the shape of a magnet. In the Orion Nebula, these field lines appear as smooth, arcing structures, threading through the gas and wrapping around dense clumps and filaments. In some areas, the magnetic fields are parallel to gas flows, guiding the collapse. In others, they're perpendicular, resisting it. This tension creates zones of balance and conflict, shaping where stars can form and where they can't. Magnetic fields can be both supportive and suppressive. In collapsing molecular clouds, gravity is trying to pull everything inward. But magnetic fields can oppose this collapse, adding magnetic pressure that supports the gas, like scaffolding around a crumbling building. If the magnetic field is strong enough, it can delay or prevent star formation entirely. If it's weak, gravity wins and collapse proceeds. In Orion, we see both outcomes. Some regions are clearly collapsing, forming stars, launching jets, feeding disks, but other regions, equally dense, remain inert. And the difference often comes down to magnetic alignment and strength. Strong fields, tightly wound around a filament, can prevent fragmentation. Weaker or more chaotic fields allow stars to form freely. There's also the matter of angular momentum. When gas clouds collapse, they spin, but they can't spin forever. Something has to remove that momentum, or else the collapsing material would fly apart like a carousel on overdrive. This is where magnetic fields come in. They act like brakes, channeling angular momentum away via magnetic torques or magnetic braking. Without this effect, planetary systems couldn't condense. Disks would be too unstable. What's even more interesting is that magnetic fields probably play a role in sending the bipolar jets out from protostars. We will talk more about these jets later. These aren't just explosive outflows. They're magnetically collimated outflows that are directed and narrowed by twisted field lines, like plasma guns going through a coil. There are a lot of them in Orion. Each one has a magnetic signature that is written in light. The Orion Nebula is also helping us refine our understanding of magnetic turbulence, how field lines interact with chaotic gas motion. Some models predict that turbulence can tangle field lines, reducing their ability to support gas against gravity. Others suggest turbulence can actually amplify magnetic strength through a dynamo-like process. Observations in Orion, especially near the Trapezium Cluster and the Bar, are giving us real data to compare against these simulations. It's not just leftovers that Orion has magnetic fields. They could have come from the space between the stars or from supernova and stars that formed in the past. Some of Orion's magnetic structure may be millions or even billions of years old. It has been stretched and changed by the birth and death of stars over and over again. It shows that the nebula is more than just a glowing cloud of gas. It's a complicated magnetic environment where unseen forces control what comes together, what breaks down, and what doesn't happen at all. We might forget about magnetism's quiet power in the face of UV light and star winds. There is it everywhere in Orion, though, setting up pillars, supporting threads, jets that guide, not falling apart, setting up worlds. Magnetism's invisible hand is at work everywhere you look. Infrared eyes on Orion, seeing what visible light can't. A lot of light can shine through the Orion Nebula, but that's not the whole story. There is a world hidden behind those bright reds and blues, a hidden landscape hidden by gas and dust where the newest stars flicker, spin, and sometimes explode into being. We need to shift how we look in order to see it. We need to stop depending on what our eyes were made to see and start using infrared vision instead. Infrared light penetrates dust the way X-rays cut through skin. In regions like Orion, where thick clouds of gas obscure most of the action, infrared telescopes are our best tools for pulling back the curtain. They reveal what visible telescopes can't: the youngest, most deeply embedded stars, the structure of cold gas, and the glow of warm dust as it absorbs radiation from newborn suns. And Orion? Orion is an infrared wonderland. When the Hubble Space Telescope first peered into the nebula, it captured unprecedented detail in visible light. But when Spitzer, and later the James Webb Space Telescope, JWST, turned their infrared eyes toward the same region, an entirely new layer emerged. Suddenly, stars previously invisible, buried inside dark cocoons, popped into view. Entire populations of protostars, some only a few thousand years old, came to life in Spitzer's detectors. We can see more than just stars in infrared data. It shows us younger ones. This is a Class 0 or Class 1 protostar. It is still covered by thick layers of gas, still gaining mass, and its light is still hidden from ordinary telescopes. Some are so young that their surfaces aren't even clear yet. Some are spitting out binary jets that can only be seen at certain infrared wavelengths. These are stars in the making, caught in the middle of giving birth. Infrared also allows us to see dust itself glowing, not reflecting starlight, but emitting its own faint heat signature. This helps astronomers map the temperature and density of gas throughout Orion. Where is it warm? Where is it collapsing? Where is it stable? In infrared, these answers become patterns, filaments of warmth, knots of pressure, and voids where radiation has already swept the area clean. The variety of protoplanetary spheres is one of the most amazing things that infrared vision has shown us. In visible light, we might be able to see the shape of a disk covering stars. But in the infrared, we can see these disks' gaps, rings, and even spiral arms, as well as their structure and heat. Some are thick and making planets right now. Others are thin and show signs of being worn down by stars close by. Astronomers use a young system's glow to figure out what stage of growth it is in. And then there's the chemistry. Certain molecules emit light only in the infrared, including water vapor, methane, carbon dioxide, and organic compounds like polycyclic aromatic hydrocarbons, PAHs. These emissions trace the building blocks of life, right there in the heart of Orion. Using infrared spectroscopy, scientists can not only identify these molecules but determine their temperature, velocity, and spatial distribution. We're not just looking at clouds, we're reading the ingredients list of star and planet formation. The James Webb Space Telescope is now pushing this even further. Its mid-infrared instrument, MIRI, and near-infrared camera, NIRCam, have revealed stunning high-resolution detail in parts of Orion previously too dusty to see. Jets, shocks, young stars, even possible rogue planets. Things once hidden are now exposed. And the level of precision is so extreme that researchers can track variability in protostars over short timescales, watching as accretion bursts or flickering shadows reveal dynamic activity inside these systems. But maybe the most important thing about infrared astronomy is that it lets us see how suns like ours are born. The big, bright cloud can be seen with the naked eye. You can see the seeds, which are quiet, shaking dots of heat that could one day be home to planets, weather, seas, and maybe even life. Infrared light breaks down the image of silence and shows us that everything in Orion is moving and changing all the time, even in the darkest places. Shockwaves and Bowshocks, when winds collide. New stars don't come in quietly in the Orion Nebula. When they arrive, they are screaming, kicking, and throwing things at very high speeds. One of the most recognizable features of the nebula is its shockwaves and Bowshocks, which are burning scars made when star winds hit their surroundings at supersonic speeds. Fuzzy poems written in arcs and lines of glowing gas. So, what are we really looking at? When young stars form, especially ones that are still gaining mass, they often send out large amounts of gas. Not just light winds, these streams are supersonic jets going hundreds of kilometers per second. They crush and heat the gas in their path as they speed through the nebula around them, creating shock fronts. The shocks ionize the material, which makes it glow at certain wavelengths, mostly in the infrared and visible ranges, along lines like hydrogen alpha and forbidden oxygen. As a result, there were glowing arcs, bands and wisps all over Orion, looking like space junk. One very interesting shape is the Bowshock, which is a bent comet-like structure that forms when the wind from a passing star hits gas that is still or moving more slowly. A star moving quickly through the nebula makes a path of light, like a boat making a bow wave as it moves through water. You can often see these Bowshocks before stars go off in a different direction or before protostars shoot out jets. They are signs of very active stars. In Orion, these shock features are everywhere. High-resolution images from Hubble, JWST, and ground-based observatories reveal hundreds of them, some tiny and faint, others sprawling across entire light years. Many are tied to specific jets or outflows from known protostars. Others are more mysterious, their origins buried in dust or long since faded. They give you information. Astronomers can figure out how fast star winds are moving, how dense the gas around them is, and even how old the outflows that made them are by measuring their shape, brightness, and speed. Some Bowshocks look like they are stacked, which means that the young star went through bursts of rapid ejection, like a cosmic hiccup. Some are off-center, tilted, or split, which shows how complicated the magnetic and gravity terrain is that they move through. In some areas of Orion, shockwaves overlap, multiple jets and winds intersect, creating tangled regions of compressed heated gas. These interactions aren't always gentle. In fact, it's believed that some of Orion's most chaotic structures, like the Orion fingers in the BNKL region, were caused by a stellar explosion or close encounter, where multiple protostars may have merged or violently scattered, launching debris in all directions. This area, sometimes called the Orion outflow, contains long, narrow jets and Bowshocks that stretch for light years, all converging on a single explosive origin point. It's a dramatic illustration of what happens when stellar infancy gets messy, and a reminder that even star formation can include sudden, violent release events. Shockwaves also play a role in shaping protoplanetary disks. If a young star's jet slams into nearby material, the resulting shock can send ripples back toward the star, altering the structure of the disk and possibly influencing planet formation. And when shocks pass through dense clumps of gas, they can compress those clumps, triggering new collapses and potentially igniting the birth of yet another star. In this way, shockwaves are both destructive and creative, stellar feedback mechanisms that keep the nebula alive and evolving. From a physics point of view, these shocks are great places to learn about hydrodynamics, how plasma behaves, and radiation cooling. Extreme differences in pressure, temperature, and density are things that can't happen on Earth inside a Bowshock. But in Orion, they happen all the time on a huge scale, over light years of space. It is possible to test the laws of energy flow in real time with every bright arc. The best part? It takes time for these systems to change. People have seen some of them change their minds in just a few decades. Astronomers can follow the path of shock fronts like you would follow a wave across the water by putting images from Hubble and JWST next to each other. Parts of space are changing so fast that we can see it happen, even though it seems like space will never end. When you see a picture of Orion with bright crescents and very thin lines, know that they're not just pretty patterns. Stars are learning how to breathe, and those waves are their first steps. The damage caused by cosmic violence, the marks left by jets and winds slamming through the stuff that made them. Bipolar outflows, the violent exhalation of newborn stars. In the beginning of its life, a star can't be quiet. A protostar doesn't just sit there and glow as it forms from gas that is falling. It does something. It fights back. It screams into the darkness through two small, sharp, at odds with each other fire and force pathways. Bipolar outflows are two jets of gas shooting out from the poles of a new star. They are one of the strongest signs that something big is about to happen. In the Orion Nebula, bipolar outflows are everywhere. Like cosmic flamethrowers, they stretch across light years, punching tunnels through the surrounding gas and leaving glowing wakes in their path. Some are subtle and faint, visible only in infrared. Others are spectacular, tearing through the nebula in arcs and streaks of shock-heated material. What exactly makes this double-barreled ejection happen? It starts with a protostar, which is a thick ball of gas that is still pulling matter in from an accretion ring around it. This disk spins and feeds the star that is growing in the middle. The gas, on the other hand, brings rotational momentum with it, which the protostar can't take in all at once. The extra energy needs a way to get out. In this case, magnetic fields come into play. As the disk spins, it twists them into a corkscrew shape that launches gas away from the protostar's poles in narrow, focused jets. These jets are fast, hundreds of kilometers per second, and they carry with them not just matter, but momentum and energy. As they punch through the surrounding cloud, they create shock waves, heating the gas and making it glow. The result is a visible bipolar outflow, often bracketed by Bowshocks at the leading edges and sometimes visible all the way back to the protostar that launched them. Some of Orion's most famous bipolar outflows come from objects like HH-212 and HH-34, Herbig-Haro objects that mark where jets have slammed into the nebula. These outflows can last for tens of thousands of years, flickering in brightness as the accretion rate from the disk fluctuates. In many cases, the outflows are episodic, meaning the protostar fires in bursts, like a machine gun instead of a fire hose. Each pulse leaves behind a knot or shock feature, giving the jet a segmented, bead-like appearance. What's remarkable is how precise these outflows can be. Despite the chaotic environment of Orion, many jets remain perfectly collimated over vast distances. This stability is thought to be maintained by the magnetic field structure around the disk, which acts like a stabilizing nozzle. In fact, studying bipolar outflows is one of the best ways to probe the magnetic geometry of a forming star's environment. But the jets don't just make pretty lines. They serve a critical function. They regulate star formation. By ejecting excess angular momentum and clearing out material from the surrounding area, they help the star avoid growing too large too quickly. In a way, the jets are like pressure valves, venting energy and allowing the core to settle into a more stable, mature state. These outflows also influence the birth of planetary systems. By carving out low-density cavities in the nebula, they can shield nearby disks from radiation, preserving their ability to form planets. At the same time, if a jet passes too close to another forming system, it can disrupt or destroy that disk entirely. So jets are both guardians and wrecking balls, depending on their aim. Infrared telescopes like JWST and ALMA have taken our understanding of these jets to the next level. In Orion, we now observe not only the gas being ejected, but also the dust entrained in the flows, the molecular composition of the outflows, and even signs of jet rotation, suggesting that angular momentum is being physically carried away in a twisting spiral. These observations are helping us connect the dots between star formation, disk dynamics, and the conditions that lead to habitable planets. Bipolar outflows also serve as timelines. By measuring the length of the jet and its velocity, astronomers can estimate when a star began accreting heavily and how its environment responded. In Orion, some outflows stretch for several light years, indicating thousands of years of sustained activity. Others are shorter and younger, hinting at a star that's just begun to breathe fire. Every flow of money is a message, something that shows resistance and growth. I'm here, it says. I'm shaping up, and I'm not leaving quietly. And sometimes, these movements change more than just one star. They change the whole neighborhood. The blast front can push down on nearby clouds, causing them to break and starting new waves of star formation. That brings us to the next big question. Triggered star formation. Does one generation spark the next? The Orion Nebula doesn't just birth stars, it provokes them. In this vast celestial nursery, one generation of stars may act as midwives, or arsonists, for the next. It's a wild idea that the violent energy of newly formed stars doesn't just clear space, but actually kickstarts the creation of new stars nearby. This phenomenon is called triggered star formation, and in Orion it's not just a theory, it's a daily occurrence. When a massive star forms, like those in the Trapezium Cluster, it unleashes an arsenal of destructive forces, ultraviolet radiation, stellar winds, and shock waves. These forces expand outward, carving cavities, eroding pillars, and lighting up surrounding gas. In their wake, they leave behind compressed ridges and pockets of denser material. And sometimes, those pockets reach a tipping point. They collapse. Gravity takes over, and a new star is born. That's what starts star formation, when feedback from one generation of stars makes a nearby area thick enough for a new generation to form. For me, it's like stars moving the torch through force. This chain reaction in space works really well with Orion. We can see bright-rimmed clouds, compressed filaments, and glowing arcs all over the nebula. These are all signs that growing shock fronts have hit gas that was already there. In many of these areas, groups of protostars have shown up, which look like they are right behind the radiation walls that are growing. As if the wave had passed, stars lit up in its wake. One famous region where this happens is along the Orion Bar, the sharp boundary we discussed earlier. Behind that glowing edge, new stars are being discovered in the compressed layers of gas. These stars appear younger than those in the trapezium, suggesting that the radiation from the older stars might have triggered their birth. It's not definitive proof, but it's compelling. In the area of Orion South, just below the Trapezium Cluster, there is another stunning example. Astronomers have seen evidence of ionization fronts and bubbles that are spreading and meeting heavier clouds here. There are protostars in those clouds. The way the space is set up strongly suggests a cause and effect link, as if the bigger stars sent out shock waves that hit surrounding gas and set it on fire. The complex look of star development in Orion might even be due to this domino effect. The nebula doesn't seem to have a single burst. Instead, it has many generations of stars, each born a little after the last and farther from the center. The beginning of one group causes the next to form, like waves in a pond. The time frame goes back millions of years, but it's easy to see the trend. Triggered star formation isn't guaranteed to work. It's a balancing act. If the shock wave is too weak, it won't compress the gas enough. If it's too strong, it can disperse the gas entirely, shutting down any chance of collapse. The conditions need to be just right. Dense enough to compress, stable enough to survive, and cold enough to fall inward instead of boiling away. Astronomers use high-resolution imaging and spectroscopic data to test these scenarios. By measuring gas velocities, temperatures, and density gradients, they can model whether a star-forming clump is collapsing under its own gravity or merely reacting to external pressure. In Orion, many clumps show the signature of compression from outside rather than internal collapse alone, supporting the idea that triggering is at play. This process isn't just for education, it changes the way the nebula is built. Chains of stars, arcs of clusters, and filaments lined up with shock fronts are all made by triggered formation. It also changes how long star creation goes on for. Massive stars die in just a few million years in places like Orion. Their supernovae may cause one last round of star births before the area spreads out fully. It's a race through space. After running for a short time, each generation gives its speed to the next and then burns out, letting the next wave take over. If Orion is any sign, this cascading pattern may be the main way that stars form in busy parts of the galaxy. Stars don't just form by themselves, they form in a series, as part of a group, or as a heritage. So while we often imagine star formation as something solitary and serene, the truth in Orion is far more explosive and far more interconnected. Every young star may owe its existence not just to gravity, but to the violent breath of the stars that came before. Molecular hydrogen emission, glowing in the dark. There is silence before stars light up and jets burst. That quiet is full of molecular hydrogen. It's the most common molecule in the universe and what stars are made of. You can find it everywhere in the Orion Nebula. You can't see it, though. It does not give off visible light. It doesn't catch fire like charged hydrogen does. It whispers instead, shining slightly in the infrared to show the quietest and darkest parts of the cosmic nursery. Molecular hydrogen, or H2, is made when two hydrogen atoms bond in cold, dense regions of gas, usually shielded from the violent ultraviolet radiation of nearby stars. These regions are cool, often just a few dozen Kelvin above absolute zero, but when something stirs them, like a passing shock wave, stellar wind, or outflow jet, H2 begins to glow. The emission isn't flashy. It appears in very specific infrared wavelengths, like fingerprints in the fog. Using instruments like those aboard Spitzer, ALMA, and now the James Webb Space Telescope, astronomers can isolate this glow and map the structure and activity of the coldest regions in Orion. It's like turning on night vision in a room you thought was empty and realizing there's motion everywhere. In Orion, molecular hydrogen emission outlines a different version of the nebula, a hidden version. Instead of the glowing arcs and hot ionized gas you see in Hubble images, H2 shows you the filaments, veins and pockets where stars are just starting to form. These regions don't shine from heat, they glow from excitation, when something, usually a shock or a strong infrared burst, causes the H2 molecules to vibrate and emit photons. The fine-grained pattern of Orion's structure is one of the most interesting things that H2 mapping has shown us. What looks like empty space between bright poles is often made up of webs of cold gas that are linked together like threads in a huge cosmic spider web. These threads can go on for light years, and they often go straight into thick groups that are making stars. In fact, H2 release can often show the exact paths of gravitational collapse. Another incredible application, tracing outflows. When a protostar launches jets, the gas around it gets shocked and heated. Molecular hydrogen reacts by glowing in arcs and bullets of infrared light, marking the path of the jet like a visible contrail. In regions like the BNKL outflow, H2 maps out the aftermath of explosive events that likely occurred just a few thousand years ago. Every glowing knot is a relic of motion, a timestamp in gas. But H2 isn't just a marker, it's a regulator. Cold molecular hydrogen determines where stars can and cannot form. If there's enough H2 in one region, and if it's dense and cool enough, gravity can collapse it into a protostar. If it's too warm or too turbulent, it won't condense. So by measuring how much H2 is present, astronomers can predict where future stars might emerge. It's a kind of cosmic weather forecast, built from infrared whispers. That being said, one problem is that H2 is extremely hard to watch directly. It's hard for it to release because it's a symmetric molecule. It needs shocks or strong UV lights to do so. This is the reason why most H2 maps use indirect tracers or look for particular lines, such as the 2.12 micron emission line in the near infrared. But when those conditions are met, the H2 comes to life, especially in Orion's rough terrain. The James Webb Space Telescope is transforming our ability to observe this faint light. With unprecedented sensitivity and resolution, JWST can detect H2 emission in small-scale filaments, pre-collapse cores, and even the inner structure of protoplanetary disks. In Orion, it's already revealing dozens of previously undetected jets, outflows, and faint protostars hidden in the dust. One scary thing about molecular hydrogen is that it's the first thing to come and the last thing to leave. H2 get together in silence a long time before a star shines. Long after a supernova blasts through a cloud, the pieces that are still there turn back into cold hydrogen and move into new strands, ready to start all over again. It's the ghost of how stars were made, the breath before the scream. Dust grains, tiny seeds of planets in the chaos. You can't see them with the naked eye, not as big as smoke particles, not as hard as ash. The Orion Nebula may have the most important parts though, and those small bits are cosmic dust grains. As the gas and stars fight, tiny particles of dust quietly move through the storm. They stick together and form the solid framework of future planets, moons and comets. They are the first thing that needs to be done to get from chaos to worlds. Dust grains in Orion are made of silicates, carbon compounds, iron and ices, depending on where they form and how they're processed. Many of them were forged in the atmospheres of dying stars, like red giants and supernovae that exploded long before Orion's stars began to form. Blasted into space, these ancient grains became part of the raw material from which the Orion Nebula coalesced. In a way, every grain of dust is a relic of a previous universe. But in the violent environment of Orion, dust doesn't just float peacefully, it's under attack. Ultraviolet radiation from the Trapezium Cluster blasts these grains with energy, heating them, eroding them, and sometimes destroying them entirely. In some areas, the dust glows from the heat, radiating in the mid-infrared, painting Orion in fiery tones invisible to human eyes. In other zones, the dust acts like a shield, absorbing radiation and protecting the cooler, denser gas behind it. This dual role, victim and protector, makes dust grains crucial to the evolution of the nebula. Without dust, molecular hydrogen couldn't form. It needs dust surfaces to bond. Without dust, gas would remain too hot to collapse, since dust helps radiate heat away, and without dust there would be no planets. In the dense disks around young stars called protoplanetary disks, dust grains are the starting point for planet formation. These grains begin to collide, gently at first, and stick together thanks to electrostatic forces. Over time they grow into pebbles, then rocks, then planetesimals, objects kilometers wide that can attract more material via gravity. Eventually some of these become planets. But that's not easy in Orion. In a quieter region of space, a dust grain might have millions of years to grow undisturbed. In Orion, that same grain might be vaporized in a few thousand years if it's too close to an O-type star. That's why the location of a protoplanetary disk matters so much. Disks near the trapezium are often truncated, their outer regions eroded by radiation. Those farther away are larger, cooler, and more likely to survive long enough to build complex planetary systems. Thanks to infrared and submillimeter telescopes like ALMA and JWST, astronomers can now measure the size, temperature, and distribution of dust grains in Orion. They've found everything from sub-micron particles to millimeter-sized pebbles, and even signs of grain growth within some protoplanetary disks. This is direct evidence that, even in this harsh environment, the first steps of planet formation are already underway. It's also dust that changes how we see Orion. The dark lines and spots seen in Hubble pictures, those are dust lanes that take in and send out light. What's making the stars near the cloud turn red? That's because dust blocks blue light, which changes the color of the stars. The famous glow of the nebula is partly caused by dust that absorbs light and then sends it back out again. But not all dust is the same. Some grains carry complex carbon chains, organic molecules like PAHs, polycyclic aromatic hydrocarbons, that might be the precursors to life's building blocks. These molecules fluoresce under UV light, and their spectral fingerprints have been detected all across Orion. It's possible that life's chemistry begins not on planets, but in dust clouds like these. There's also growing evidence that comet-like objects could form early, while dust is still embedded in dense pockets of gas. These icy bodies might be the delivery systems for water and organics to rocky planets, the seeds of oceans and atmospheres. And in Orion, we may be watching that process begin. So even though dust grains look small and unimportant, they are not. They are the basic blocks of complexity, the rocks that every rocky world, including ours, is made of. They're not bright, they don't roar, but in the quiet shadows of Orion, tiny bits of dust are building the future, which is the most important job of all. CO maps, mapping the invisible cold gas in Orion. The Orion Nebula is beautiful and hot, but its real power source is cold. Under the bright ionized gas and flashing stars is a huge pool of molecular matter that can't be seen. It's cold enough to block light, but thick enough to make stars. Astronomers don't look for things that shine. Instead, they listen for things that speak. And the word of choice, CO, stands for carbon dioxide. CO is made up of only one carbon atom and one oxygen atom, so you might not think it would be a big deal in the universe. But CO is one of the best ways to find molecular hydrogen, H2, in the coldest and darkest parts of Orion. H2 is the gas that makes stars. Why? Because H2 is almost unnoticeable most of the time, even though it is the most common molecule in the world. At temperatures that are typical of molecular clouds, it doesn't give off a lot of light. CO does, though. Carbon monoxide emits at radio and submillimeter wavelengths, especially a key line at 115 gigahertz. When gas clouds get just cold enough, usually between 10 to 30 Kelvin, CO molecules begin to vibrate and rotate, releasing tiny packets of energy. Telescopes like ALMA, IRAM, and JCMT tune into these frequencies and capture that glow, turning what's otherwise a black void into a detailed map of structure, motion, and mass. In the Orion Molecular Cloud Complex, Colorado surveys have revolutionized our understanding of the region. What looks like a single nebula in visible light is actually part of a giant interconnected structure spanning over 240 light-years, full of filaments, bubbles, knots, and cores. And it's in CO emission that we see the true shape of the beast. By mapping carbon monoxide, CO, astronomers can spot where stars are forming by tracing dense gas filaments, see bubbles and cavities created by stellar winds or supernovae, track the motion of gas flowing toward or away from us, and identify clumps with enough mass to collapse into new stars, or even entire star clusters. In Orion, the CO maps reveal structures like Orion A and Orion B, two massive clouds brimming with raw material. These maps show how the Trapezium Cluster and other massive stars have carved holes and channels into the surrounding molecular cloud, pushing the gas into compressed ridges where triggered star formation may now be happening. And it's not just about seeing. CO maps are also time machines. By measuring the Doppler shifts in CO lines, astronomers can determine how fast the gas is moving and in which direction. These velocities help reconstruct the three-dimensional structure of the nebula. Are those stars really close together, or just overlapping from our point of view? Are those filaments collapsing, rotating, or dispersing? CO answers those questions. Even more interesting is the fact that some areas show signs of outflows, which are binary jets sent out by new stars. A lot of the time, these jets pick up CO molecules and speed them up, leaving high-speed marks in the CO spectrum. Researchers can find protostars that are too deep to see directly by mapping these and using the fingerprints of the gas they've stirred up to do so. And then there's the matter of CO depletion. In the coldest, densest pockets, those just about to collapse, CO can freeze out onto dust grains, disappearing from the gas phase. When that happens, astronomers know they're looking at a region that's on the verge of star formation. This chemical silence, oddly enough, becomes a clue in itself. The combination of CO maps with infrared and optical data gives us a multi-layered view of Orion. Visible light shows us the nebula's skin. Infrared peels back the dust, but CO maps, they show us the bones and veins, the underlying structure that holds the entire cloud together. Thanks to wide-field surveys from telescopes like Nanten and FCRAO and high-resolution maps from ALMA, we now understand that Orion is not just a site of starbirth, but a dynamic network of flows, filaments, and feedback, and CO is the language that reveals it. When you see a picture of the Orion Nebula that glows, know that beneath the beauty is a cold, secret structure. Chemists, not light, can follow an unseen web of gas. We can use CO to make maps of the areas where stars are growing. Buildings are falling apart, and sparks are still waiting to happen. PAHs, the complex chemistry of nebula dust. Most of the time, chemistry that makes us think of life is not what comes to mind when we think of space. But there is an amazing event going on in the middle of the Orion Nebula. There are complex molecules quietly collecting ultraviolet light and glowing in the midst of the shock waves, radiation storms, and gas that is falling. These aren't the things that make stars. They are called polycyclic aromatic hydrocarbons, or PAHs, and they are more complex. You can think of PAHs as cosmic carbon rings, flat molecules made of fused benzene-like structures, sometimes with added hydrogen atoms. Structurally, they're similar to soot or the burnt edges of toast. But in the Orion Nebula, they're floating freely in the interstellar medium, clinging to dust grains and drifting through radiation-rich space. And when ultraviolet photons from stars like those in the Trapezium Cluster strike them, these molecules fluoresce, emitting infrared light in very specific wavelengths. This fluorescence makes PAHs detectable. In fact, some of the glowing regions in Orion that appear so vibrant in mid-infrared images owe their shimmer to the presence of PAHs. Instruments aboard telescopes like Spitzer, ISO, and JWST pick up these emissions as broad features at 3.3, 6.2, 7.7, 8.6, and 11.3 microns. These are known as aromatic infrared bands, and they act like neon signs in the fog, marking where chemistry is happening, even if we can't see the molecules directly. The fact that PAHs are organic molecules makes this even stranger. They are made up of carbon and hydrogen grouped in complicated ways that are hard to make in wild places. Still, here they are, shining in one of the galaxy's most chaotic areas for making stars. The fact that they exist shows that complex chemistry can form before planets, stars, or even disks settle down. In Orion, PAHs are concentrated along the edges of molecular clouds, especially in regions called photodissociation fronts, the same zones where ultraviolet light is just beginning to bite into cold gas. These are boundary layers where the energy is high enough to break apart simple molecules, but not so destructive that it completely obliterates organic material. That sweet spot is where PAHs thrive. Their presence has several important implications. First, PAHs affect how energy moves through the nebula. They absorb high-energy UV light and re-radiate it as lower-energy infrared light, effectively cooling the gas and helping regulate the temperature of star-forming regions. This isn't just a side effect, it's a critical part of how these regions maintain balance. Second, PAHs may be part of the chemical pathway toward life. In lab settings and meteorite samples, PAHs have been shown to interact with other molecules to form amino acids, nuclear bases, and even prebiotic compounds. If these molecules can survive in Orion, they might also be carried onto dust grains that form protoplanetary disks and eventually planets. In that sense, Orion isn't just a stellar nursery. It might also be seeding the galaxy with the building blocks of biology. Third, PAHs give astronomers a new way to trace the structure of the nebula. Because they glow in very specific conditions, just at the margins between hot and cold gas, they mark out the shapes of radiation fronts, filaments, and cavities. By mapping PAH emission, we can better understand where feedback from massive stars is changing the chemistry of the surrounding cloud. But PAHs don't last forever. If exposed to too much radiation, they can break apart, especially smaller ones with fewer carbon atoms. That means PAH distribution across Orion also tells us how violent a region is. Areas with lots of intact PAHs are relatively calm or shielded. Regions where PAHs are absent, likely scorched by intense UV light or swept away by winds and shocks. The James Webb Space Telescope is currently offering the most detailed look yet at PA8s in Orion. With its powerful spectroscopic instruments, JWST can not only detect PA8s but identify variations in their structure and composition, giving us clues about the chemical evolution of the nebula over time. In the heart of this cosmic furnace, where stars are born in fire and gas is torn apart by light, there's something fragile and surprisingly Earth-like. Carbon rings that glow softly and float on dust grains, giving us a taste of what's to come. They are the chemical mark of possibility. They are small but strong. They move through Orion like seeds with no Earth yet. However, these molecules that glow are only a small part of the bigger picture. Light from the nebula makes it to Earth, but not before going through a strange, partly clear layer that bends what we see and gives us a hint of a structure with more layers than we thought possible. The veil of the Orion Nebula, foreground dust structures. The Orion Nebula is very bright, but it's not as clear as it seems. There is a thin layer of dust between us and the bright gas that is easy to miss. This isn't really a part of the bright cloud, but it is connected to it in some way. The light that reaches Earth is filtered, dimmed and bent by this partially clear upper layer. It turns out that this veil isn't just an eye annoyance. It's a mask that shows the shapes of something much deeper within the nebula. Astronomers first suspected the presence of this veil because of a strange mismatch between observed brightness and expected emission. Some areas of Orion seemed too faint, others oddly red-shifted or blue-shifted. When scientists looked closer using spectroscopy and polarization, the culprit became clear. A thin, uneven sheet of dust lies between Earth and the Orion Nebula's core, like a fogged glass pane between you and a neon sign. This veil, made of fine interstellar dust grains, doesn't block light completely. It absorbs some, scatters more, and reddens everything behind it. Shorter wavelengths, like blue and violet, get scattered away, while longer red and infrared wavelengths pass through more easily. This is why stars near Orion often appear redder than they truly are, an effect called interstellar extinction. By measuring how different colors are absorbed, astronomers can map the thickness and texture of the veil itself. The veil isn't flat. It's rippled, folded, and clumped, with some areas only a few light months thick and others stretching across several light years. These ripples are not random. They're shaped by the same forces that shape the nebula behind them: radiation pressure, stellar winds, and gravity. In fact, the veil may be interacting with the expanding ionization front of the Orion Nebula, forming a kind of buffer zone where ionized and neutral gases meet and mix. Some areas of the veil have been pierced by protostellar outflows, creating tunnels of low extinction where we can peek more deeply into the nebula. Others are dense enough to block even near-infrared light, hiding entire clusters of young stars that can only be revealed through mid-infrared or radio observations. This makes the veil both a challenge and an opportunity, a filter that hides and reveals, depending on how and where you look. And yet, the veil may be most useful because it helps us figure out how Orion is built in 3 dimensions. Astronomical pictures are usually flat, showing large areas of space in 2 dimensions. Scientists can figure out how far apart different parts of the nebula are by measuring how much dust is absorbed in the foreground and how much is emitted in the background. It was thought that some strands were inside the main cloud of light, but now we know they are in front of it, making shadows like smoke moving between a fire and a lens. These findings reshape how we model Orion. Instead of a flat canvas of gas, we now see it as a layered sculpture with dense filaments behind glowing arcs, cavities bored out from both sides, and a veil that shifts and changes our perspective. It's as if the nebula is wearing a semi-transparent mask, one that must be peeled away piece by piece to understand the true depth beneath. New studies using JWST's infrared capabilities are now revealing fine-grained patterns in the veil, including streamers of dust, polarization gradients, and magnetic field alignments. These features suggest that the veil itself may be part of a larger magnetic and structural framework, possibly connected to the Orion Eridanus superbubble, a massive structure that envelops the nebula from behind. The Orion Eridanus superbubble, a galactic shockwave zone. Take a step back from the Orion Nebula's bright chaos and look at something bigger, a lot bigger. There is a huge, almost transparent ring of hot gas around Orion that goes out hundreds of light years and looks like the ripples from an old explosion. The Orion Eridanus superbubble is this, and it's not just a background for the nebula. This place is an important part of the history of this area and will continue to be so in the future. The Orion Eridanus superbubble is a giant cavity in the interstellar medium filled with tenuous, superheated plasma. It stretches from the Orion constellation into the neighboring Eridanus constellation, covering an estimated 1,200 light-years in diameter. The bubble is so vast, it dwarfs the Orion Nebula itself, which sits nestled inside its edge, like a spark flaring up inside a scorched crater. How did it come to be? Supernovae are the best explanation. There might be dozens of them. In the last 10-15 million years, big stars in Orion's older stellar associations, like Orion OB1A and OB1b, have lived short lives, died young, and burst with enough force to make a hole in the space between the stars. Each supernova would have given off huge amounts of energy, which would have sent shock waves out into space, and gathered gas and dust into a huge, growing ring. The superbubble is what's left. A low-density, high-temperature center ringed by a thicker shell of material that has been swept up. The bubble gives off a faint glow in X-rays, radio waves, and some ultraviolet lines. It can also be seen in part as Barnard's Loop, a bright red arc on the eastern side of Orion that looks like a cosmic halo. This structure isn't static. It's still expanding, albeit slowly now. And that expansion is interacting with the Orion molecular cloud complex, compressing some regions, dispersing others, and influencing how and where new stars are born. In other words, the superbubble may have helped trigger the very star formation that gave rise to the Orion Nebula. It's a feedback loop that spans millions of years and hundreds of light years. Astronomers detect the bubble not just through images, but through velocity maps. When they measure the motion of gas using CO or H-alpha emission lines, they see clear signs of expansion. Gas on one side of the bubble moves toward us, on the other, it moves away. The shape is asymmetric, more like an open-ended shell than a perfect sphere, likely due to interactions with other structures in the galactic plane. The way the superbubble may have punched through the galaxy disk is very interesting. There is evidence that the bubble is losing matter into the galaxy halo, which is sending hot gas high above the Milky Way's plane. This process might help explain how galaxies move gas into and out of their star-forming regions. This means that superbubbles like Orion Eridanus are important to the history of galaxies. And Orion isn't alone. The galaxy is littered with superbubbles, giant scars left behind by clusters of massive stars. What makes Orion Eridanus special is that it's so nearby, so active and so well studied. It offers a rare opportunity to examine how massive star death influences massive star birth, all in one interconnected region. It looks like new superbubbles are even forming inside the old shell. Some of the Trapezium Cluster's big stars, like Theta 2 Orionis C, will likely go supernova in the next few million years as the cluster gets older. When that happens, they'll send even more energy into the area, which could cause stacked shock waves that change the shape of the building all over again. In other words, Orion is not alone when we talk about it as a star nursery. It's making stars in the dark of old blasts, in a cosmic wound that can still breathe. People have been hurt by the Orion Nebula, and it is also making the next wave worse. The proof is the superbubble that's around it. Every glowing ridge, every compressed filament, every protostar flickering into view. It all happens under the influence of this vast, invisible dome. The superbubble isn't just the past. It's the current stage, the set design, and soon maybe, the spark for the next act. At rotation. Do protostellar jets spin? Already, jets from new stars are very impressive. They shoot gas through the Orion Nebula at hundreds of kilometers per second, like cosmic weapons. However, what if those jets aren't firing in a straight line? What if they're spinning? It may seem like a small thing, a twist, but if it's true, it could prove something very important: how stars and ultimately planets lose and gain rotational momentum. In Orion, these protostellar jets, launched from stars still forming in dusty envelopes, are everywhere. We see them as long, narrow streaks in visible and infrared light, marked by glowing knots and shock fronts. But the structure of these jets isn't uniform. Some appear to have asymmetries, others seem to corkscrew slightly, and in a few rare cases, there's direct evidence that they may actually rotate as they shoot out into space. What does that matter? Because it's all about rotational motion, which is like a figure skater pulling in their arms to make the spin go faster. It spins when a huge cloud of molecules falls apart to make a star. Because of the law of conservation of rotational momentum, the cloud spins faster and faster as it gets smaller. What's wrong, though, is that a falling protostar would tear itself apart before it could fully form if it kept spinning without being stopped. That extra spin needs to be taken care of somehow. That's where jets come in. Theoretical models suggest that jets are launched by magnetocentrifugal forces, magnetic field lines anchored in the star or disk that fling material outward along the star's rotational axis. If that's the case, then jets shouldn't just move fast. They should carry away some of the system's spin. In other words, jets should rotate. You're looking for very small changes in speed across a structure that's only a few astronomical units wide, and is usually hundreds or thousands of light years away. But now that we have strong spectrometers and high-resolution interferometers like JWST and ALMA, we have data that is clear enough to see the twist. Astronomers have found small changes in the Doppler shift across the width of some jets in Orion. One example is the jets coming from HH 212, which is a very uniform and narrow bipolar jet. It looks like one side is moving toward us and the other side is moving away. Only a few kilometers per second separate them, which is small but in line with what we'd expect from the jet spinning on its axis. This detection, while still debated in some circles, supports the theory that jets act as angular momentum exhaust valves, not only ejecting mass from the star disk system, but also spinning off excess rotational energy. That means these outflows are essential to star formation, regulating how quickly and safely a star can form, and whether a disk can survive long enough to form planets. If this mechanism holds across most protostellar systems, it would also help explain the observed rotational speeds of young stars. Without some way to shed angular momentum, newborn stars would spin much faster than we observe. Jet rotation offers a clean, physics-backed answer. It changes more than just the science of these streams, though. They're not just fire hoses. They're structures that twist and turn, maybe even braided with magnetic fields. Some computer models show that these rotating jets might create spiral shocks as they interact with their surroundings, which could even have an effect on nearby cores that are falling. That is, a spinning jet might not only make a hole in the cloud, it might also carve a circle into it. In some cases, we see signs of instability in the jets that might be linked to rotation. For example, knots that break off, wiggles that follow corkscrew paths, and even binary systems where each protostar fires off jets that rotate counterclockwise. Orion shows many examples of these strange combinations, so scientists can check their theories against what they see, case by case. It's also possible that these early twists have long-term implications. The direction and strength of angular momentum ejected via jets could influence how disks evolve, how planets form, and even how multiple star systems arrange themselves. In a way, the earliest moments of stellar breath might dictate the layout of entire planetary systems. Jet rotation isn't easy to see. It doesn't light up like ionized hydrogen or shock waves, but it's encoded in the subtle shifts of spectral lines, a twist in the light itself, revealing a hidden dance beneath the blaze. Stellar cannibalism, close encounters in the core. The Orion Nebula looks like a party at first glance, with its bright stars, glowing gas, and new star systems lighting up the darkness. But something darker might be going on deep inside, where the stars are very close together and could be dangerous. Gravitational lines become less clear in these crowded areas, and when stars get too close, they fight, steal, and sometimes eat each other. Here we are on the cutting edge of star eating. Now, to be clear, stars don't literally bite chunks out of each other like cosmic monsters. But in regions like the Trapezium Cluster, where stars are born just a fraction of a light year apart, gravitational interactions can become so extreme that young stars begin to distort, strip, and even merge. These interactions can change a star's path, its growth, and the future of everything orbiting it. The Trapezium Cluster in Orion is ground zero for this kind of chaos. It contains hundreds of young stars within just a few cubic light years. Some are still forming, still surrounded by protoplanetary disks. Others are already ejecting powerful winds. But the space between them is small, smaller than the distance from our Sun to Pluto in many cases. That means their gravitational fields overlap, creating a dynamic ballet with unpredictable moves. In the crowded chaos of star-forming regions, two major outcomes often unfold. First, disk striping happens when stars pass too close, within a few hundred astronomical units, and their gravity tears material from each other's disks. This can completely halt planet formation, leaving once promising stars with only narrow dust bands or nothing at all. Even more dramatic are stellar mergers, where two protostars come so close that their outer layers mix. If they spiral in fast enough, they combine into a single, larger star. These violent collisions can unleash shock waves, jets, and glowing flares that ripple through the surrounding gas. There is real proof that this has already happened in Orion. Astronomers have found what they think is the remains of a stellar dynamical interaction in the BNKL region, which is just behind the Orion Nebula. This interaction could have been a crash or split of several stars. A group of very large stars is hurtling away from a central point at very high speeds, like pieces from an unidentified explosion. At the same time, a huge overflow called the Orion Fingers shoots out in all directions. This may be the most powerful event in Orion's recent history, a cosmic sign that stars left behind when they got too close. These kinds of events may not be rare in massive clusters. In fact, they may be necessary to explain the formation of the most massive stars, those 50, 60, even 100 times the mass of the Sun. Current models suggest that stars this large may form only through mergers of smaller protostars. In a dense environment like Orion, where random encounters are inevitable, these mergers could be the missing piece of the stellar puzzle. Stellar cannibalism also helps explain the existence of runaway stars, objects that seem to have been ejected from clusters at high speeds. These high-velocity stars could be former binary companions that were slingshotted during a close three-body interaction. Some of these stars now fly solo through the galaxy, carrying the scars, or momentum, of a cosmic breakup. Even smaller-scale encounters can be devastating. A star with a developing planetary system could have its outer planets ripped away, or its orbiting dust cloud might get tilted, twisted, or shredded entirely. The implications for planet formation are massive. Entire worlds may be prevented from forming, or worse, torn from their stars before they even stabilize. And all of this happens in near silence. From Earth, we don't hear the scream of colliding stars. We see the evidence afterward, the odd velocity, the missing disk, the sudden jet, the unexpected flare. Like detectives at a crime scene, astronomers reconstruct what must have happened based on gravity's fingerprints. While stars don't usually eat each other, in Orion's heart, it may be a normal part of how stars live their lives. Born close, pushed around a lot, and formed by chance. It's a battle of the gravitational best, and the winners aren't always peaceful. Infrared variability in protostars. Twinkling stars in the womb. Stars are often thought of as steady lights in the sky that don't move or flash, but flickering is normal in the Orion Nebula, where stars are just starting to form. In the infrared, a lot of protostars act like unsteady candles. They flash on and off, getting brighter and darker and pulsing, sometimes randomly and often dramatically. These changes aren't just noise. They show us how unstable the lives of stars are while they are still in the womb. This phenomenon is known as infrared variability, and it's one of the most dynamic signals in all of star formation science. Protostars, those embryonic stars still wrapped in gas and dust, emit most of their light in the infrared spectrum because their surroundings are too cool and too obscured for visible light to escape. When astronomers point infrared telescopes like Spitzer, Herschel, or JWST at Orion over long periods, they find that many of these infant stars are far from stable. They're twinkling in the dark, and each flicker has a story. So what causes this variability? In most cases, it comes down to changing accretion rates. Protostars grow by pulling in material from their surrounding disks. But this process isn't smooth. It's bursty, sometimes irregular, and driven by instabilities in the disk. When a clump of gas spirals inward and hits the protostar, it releases an accretion burst, a sudden spike in luminosity that makes the star briefly shine brighter in the infrared. These bursts can last from hours to months, and they're not rare. In Orion, they've been observed in dozens of young stellar objects, sometimes increasing brightness by factors of 2, 5, or even more. One type of extreme case is called a Fu Orionis event, where a protostar's brightness increases by over 100 times and stays elevated for decades. While rare, these events may be a crucial part of stellar growth, dumping large amounts of material onto the star in short, explosive episodes. But there are other reasons why things can be different as well. Some protostars flash almost every so often. This is probably because of spinning clumps or warps in the inner disk. These structures go around the star and sometimes block or reflect its light, making it get dimmer and brighter in a pattern that looks like a lighthouse beam spinning through a thick fog of dust. The changes could sometimes be caused by magnetic activity or stellar spots, which are cool areas on the protostar's surface that move in and out of view. These are proofs that the star's behavior is already being shaped by magnetic fields, even before hydrogen fusion starts in full force. There is a very strange type of change that can be seen in Orion: flickering shadows. High-resolution infrared images show that some disks make moving shadows on the gas around them, as if something inside the disk is moving quickly and blocking light. This might happen because thick groups, spiral arms, or even protoplanets are messing up the structure of the inner disk. Monitoring these changes requires patience and consistency. That's why telescopes like Spitzer's Young Stellar Object Variability programs have stared at Orion for weeks or even months at a time, capturing the light curves of hundreds of forming stars. These long-term datasets reveal patterns. Some stars are quietly variable, others explode with light. Some have flat, boring curves. Others look like heartbeats, like storms, like Morse code from stars that haven't even finished forming. But what's really cool is that these flickers show a growth timeline. When scientists watch how a protostar's brightness changes and compare it to the shape of its disk and jets, they can figure out how the star is eating, what its surroundings look like, and even how likely it is that planets will form later on. Variability isn't a bug, it's a checkup. And in Orion, where stars form in clusters, infrared variability also helps astronomers identify which stars are truly young and still accreting. This is key in separating mature background stars from true protostars, especially in such a crowded and layered environment. In a way, these tiny lights in the sky are the sound of stars breathing. Bursts, hiccups, and flickers are all signs that help us understand how mass builds up, how systems stay stable, and how the galaxy slowly turns gas into light. Is there a black hole in the Orion Nebula? It sounds like science fiction, or maybe even a bit of it. A black hole hiding in a cloud where stars are being formed? Could something built on death be hidden in plain sight in a place that shines with new life? As a surprise, some scientists say, maybe. It hasn't been proven yet, but there's more and more proof that the Orion Nebula might hide a small black hole or the remains of a fallen star somewhere deep inside. It could be hidden by the bright gas and fast, chaotic motion. So where does this idea come from? It starts with anomalous motion. In some parts of Orion, particularly near the BNKL, Becklin-Neugebauer/Kleinman-Low region, astronomers have observed high-velocity stars and shock waves that don't quite make sense. Several stars in the area are racing away from a central point at speeds of up to 30 km/s, and the surrounding gas shows signs of a massive explosion or interaction that may have happened about 500 to 1,000 years ago. A possible reason? A system with many stars became gravitationally unstable. This caused a violent interaction in which one or more stars were thrown out, and something else, maybe a black hole, formed from the chaos. There's also the possibility that one of the stars in the older Orion OB associations, massive stars born millions of years before the current generation, already went supernova, collapsing into a black hole or neutron star, and blending into the cloud. If that object didn't receive a large kick, it could still be there today, nearly invisible except for its gravitational influence. What would Orion's black hole look like? In reality, it most likely wouldn't look like anything. A black hole with the mass of a star, especially one that isn't actively eating, wouldn't give off light. It wouldn't change the gas around it in a way that could be seen. But its gravity would pull on stars and gas close by. It could even change the tracks of protostellar jets, or make gas strands have strange differences in speed. Some simulations of the BNKL outflow suggest that an unseen mass, possibly in the range of 3 to 5 solar masses, would help explain the violent ejections we observe today. That range is squarely within the lower limit for a stellar black hole. Not a supermassive monster, just a quiet, dense object that bends space and slumbers in the dark. Some people say a neutron star is a better choice. It's still strange and scary, but not quite as final. Still others believe that there is no need for a compact residue at all. They believe that the explosion and fast-moving stars could be explained by the random interactions of many young stars in a close cluster. A lot of people are debating this topic, and Orion is the right place to test these wild ideas. As astrometric accuracy has grown thanks to projects like Gaia, scientists can now precisely trace the paths of stars in Orion and measure their speed and acceleration in 3 dimensions. If there is a secret mass, something big and invisible, its gravitational pull might finally show up as small, strange changes in the way stars move. There's also the possibility of detecting a black hole companion. If one of the stars in Orion is orbiting an unseen object, its motion might wobble in a detectable way. These are the kinds of signs that helped confirm the existence of black holes in binary systems elsewhere in the galaxy. And now, the same techniques are being turned toward Orion. The discovery of a black hole in the Orion Nebula wouldn't just be a cool twist. It would be profound. It would suggest that in the very places where stars are born, the remnants of earlier deaths still linger, possibly influencing the next generation. It would also reshape how we think about the life cycle of star-forming regions, revealing that destruction and creation may be far more intertwined than we imagined. Even if there isn't a black hole there now, Orion may soon make one. Stars like Theta 1. Orionis C are massive enough to go supernova within the next few million years. When they do, they'll leave behind neutron stars or black holes of their own, adding fresh gravitational ghosts to the nebula's future. So is there a black hole in Orion? We don't know yet. But the fingerprints are there. The stars are moving strangely. The gas is exploding in ways we didn't expect. And in a region full of beginnings, the shadow of an ending may already be here. How dense is too dense? The limits of star formation in clusters. There are so many stars in the Orion Nebula that it's easy to think that more density always means more being made. Gravity, after all, likes things to be close. Gas falls apart faster when it is packed together tightly. There is a catch, though. Strange things start to happen in places like the Trapezium Cluster, where stars are almost touching each other. Star creation starts to slow down. It's not that the fuel runs out, but that the environment gets too harsh for new stars to grow. One of the most interesting points in astronomy is the point where density stops being helpful and starts being harmful. It makes no sense. When pushed too far, the factors that make stars form, high pressure, gas that is packed tightly, and fast gravity acceleration, can start to stop more formation. This is especially clear in the center of the Trapezium Cluster in Orion, where big stars take up most of the scene. Their radiation makes holes in the space between them. Their winds blow stuff around, and their gravity makes the stars and gas around them move in a crazy way. There isn't just less space. The balance of forces is lost. New stars form best when cold gas can gather and collapse in peace. But when the region becomes too dense, temperature rises, collisions increase, and external pressures begin to override local gravitational instabilities. The gas gets squeezed, but not in a way that helps it collapse. Instead, it can be heated, shredded, or even pushed outward entirely. This is known as Jeans instability regulation, named after the physicist James Jeans. There's a critical mass and temperature at which a gas cloud can collapse. But in ultra-dense environments, heating from nearby stars can raise the gas temperature just enough to stabilize it, ironically making it harder to fragment and form new stars. Another limiting factor, tidal forces. In dense clusters, the gravitational pull from neighboring stars becomes significant. If a forming star or disk gets too close to a more massive neighbor, it may be torn apart or disrupted before it even finishes forming. These interactions reduce the efficiency of star formation and may result in a higher number of failed stars or ejected objects, like rogue planets and brown dwarfs. We can see this barrier in real time through Orion. Around the edges of the nebula, where the gas is less turbulent and the stars are farther apart, stars are still forming in quiet groups. At the core, though, you can see signs of repression. Disks are cut off, jets are bent. There are fewer and more spread out young stars. The world turns against frailty. Also, a cluster like Orion can only keep making stars for a certain amount of time. When the largest stars go supernova, they release enough energy to break up the gas around them. That time is probably still a few million years away in Orion, but it's getting closer. And when it does, the compact cluster will run out of raw materials and no more stars will be made. An orange shell, a dozen young stars, and maybe one or two black holes will be all that's left. So how dense is too dense? There's no single number, no magic cutoff. It depends on temperature, magnetic fields, radiation, and turbulence. But in general, when the density of a region exceeds its ability to cool, or when stars are so packed that their feedback overwhelms gravity, formation grinds to a halt. That's where Orion is dancing. Some places can still grow crops. Some people are getting tired. It is a plant that is getting close to shutting down, not because of a lack of materials, but because it is so successful. There were too many births of stars too quickly, and now the process that made them is starting to fall apart. Chemical fingerprints of Orion, tracing starbirth recipes. It's possible to dip a space spoon into the Orion Nebula and taste it. What would the spoon be made of? Hydrogen and helium are the two most abundant elements in the universe. But Orion's bright clouds are also made of oxygen, sulfur, nitrogen, carbon, and iron, which were cooked in the centers of stars. And just like a fingerprint, Orion's chemicals tell a story. They tell us not only what it is, but also how it formed and what kinds of stars it can make. Astronomers call this field astrochemistry, and in places like Orion, it's the ultimate lab. By analyzing the light, specifically the spectral lines emitted by atoms and molecules, we can read the entire ingredient list. Every element glows at specific wavelengths when energized, and each of those glowing barcodes gives us a clue to the nebula's contents. Oxygen, for example, is one of the most prominent fingerprints in the Orion Nebula. It shines strongly in doubly ionized form, especially in the famous greenish hue often seen in long-exposure images. These emissions are more than just pretty. They indicate regions of intense ultraviolet radiation where high-energy photons from massive stars strip electrons from atoms and trigger glowing cascades of energy. Sulfur, another key player, tends to glow in the red part of the spectrum. Its lines are typically found in the outer edges of ionized regions, offering insight into how radiation fronts move outward, stripping and exciting gas along the way. These outer zones are crucial because they mark the transition from fully ionized H2 regions into colder molecular gas, where stars are still forming. And then there's nitrogen, a tracer of both warm ionized zones and cooler pockets nearby. It helps bridge the gap between the hot, violent inner nebula and the cold, dusty outskirts where star formation is just beginning. These chemical gradients, oxygen close in, nitrogen and sulfur farther out, form a kind of elemental topography, mapping the journey from violent starlight to quiet collapse. One of the best things about these spectral marks is that they can teach us about metallicity, which is the amount of elements heavier than helium in a certain area. Metallicity changes how stars are made, the kinds of worlds they can make, and how long they live. Orion has a fairly high metallicity compared to other galaxies. This suggests that it is part of a later generation of star-forming clouds that have already been boosted by supernovae and stellar winds. These supernovae are likely from the nearby Orion OB1 association, which includes aging massive stars that may have seeded the region with heavy elements millions of years ago. Their deaths added iron, calcium, aluminum, and other complex building blocks that now circulate within the nebula's gas and dust. In other words, Orion didn't form from scratch. It was recycled. That recycling process has far-reaching implications. For one, it means Orion is capable of forming rocky planets, not just gas giants. Elements like silicon, magnesium, and carbon, all critical for building solid planetary cores, are present in abundance. And with infrared observations, we can detect carbon monoxide, water vapor, and even complex organic molecules like formaldehyde and methanol. These aren't just signs of chemistry, they're potential precursors to life. The spectral lines also let us measure temperatures, densities, and ionization states. Hotter zones emit different lines than colder ones. Denser clumps show up with broader or more intense emissions. By cross-referencing these data points, astronomers can build three-dimensional models of the nebula's structure and simulate the chemical environments where stars are being born. The fact that Orion's fingerprints don't match those of every other galaxy makes it even more interesting. Each area where stars are being born has its own unique features that come from its past development, its local environment, and even the size of the galaxy arm it's in. That means Orion can be used as a standard to compare it to other places in the galaxy, like the Eagle Nebula, the Carina Nebula, or parts of the Large Magellanic Cloud. These fingerprints also change over time. As stars form, evolve, and die, they release new material back into the nebula, gradually shifting the ratios of key elements. Observing Orion across decades lets us catch these changes in action, a kind of long-form chemical weather report, updated in real time by telescopes like ALMA and JWST. It's not just light and gravity when we say that stars are born in Orion. Of course, it's also about science. The exact mix of elements that determine how hot a star burns, how long it lives, and what kinds of worlds might form around it in the future. Each ghostly line is a whisper from the past, and each part is a sign of what's to come. Stellar feedback, when stars fight back against their cradle. In the Orion Nebula, stars aren't just silent leftovers of gas falling apart, they're also changing things. As soon as a big star is born, it starts to change the shape of the cloud that made it. This is called stellar feedback, and it is one of the most powerful and upsetting forces in places where stars are being formed. This is where resistance meets gravity, when the world fights back against itself. Oh, and the battlefield is everywhere in Orion. At the center of this rebellion is Theta 1 Orionis C, the most massive and luminous member of the Trapezium Cluster. Just one star, but its radiation output is thousands of times more powerful than our sun's. It pumps out intense ultraviolet light, capable of ionizing vast volumes of hydrogen and turning cold, dark clouds into glowing H2 regions. This light strips electrons from atoms, heats surrounding gas to over 10,000 degrees, and sends shock waves rippling through the nebula. But feedback isn't just light, it's wind. Massive stars like Theta 1 Orionis C unleash stellar winds, streams of charged particles moving at hundreds or even thousands of kilometers per second. These winds slam into nearby gas and dust, carving out cavities, bubbles, and Bowshocks. In Orion, these structures are everywhere. You can trace their arcs and filaments like fingerprints of a cosmic brawl. The feedback doesn't just change the scenery, it also decides who will be born next. Dense groups of gas that could have collapsed into new stars are torn apart or squished together. In some cases, that squeezing can actually cause new stars to form, which is known as a chain effect. Most of the time, though, the pressure is too high. Before the gas can fall apart, it is heated, spread, or photoevaporated, which cleans up parts of the nebula. This push-pull dynamic is what makes Orion so fascinating. It's not a peaceful nursery, it's a battlefield between old stars and new ones, between gas trying to come together and radiation trying to tear it apart. We can see this in the region's Proplids, those tiny teardrop-shaped objects that are actually young stars surrounded by disks of planet-forming material. Many of them are being eroded in real time by UV radiation. Their outer layers are literally boiling off into space, creating bright tails and arcs pointing away from the trapezium. Some of these disks might survive, others won't. It all depends on how quickly they can grow before the environment rips them apart. And the effects aren't limited to a single star. Orion's entire central region is a feedback complex, where multiple stars, massive and intermediate, are influencing the gas at once. The result is an incredibly dynamic environment, with waves of star formation starting, stopping, and restarting across different zones. In the long run, this input helps the body regulate itself by itself. More energy is added to the cloud as more stars form. In some places, that energy stops further fall, while in others, it speeds it up. The nebula turns into a mix of options, with some areas full of new stars and others empty and blown out. And when the biggest stars die, they don't stay quiet. In Orion's future, a supernova could release enough energy to burn up all the gas left in the area, stopping the process of star formation there for good. In a strange way, the stars that make Orion beautiful today might be the ones that block it out tomorrow. But these stars are still changing their home every second before the curtain goes down. Feedback isn't just a result. It can shape, break, and even give birth. The Orion Nebula is such an interesting paradox because it is a place of birth that was shaped by forces of death. Outflow cavities, scooping out space with jets. Young stars in the center of the Orion Nebula aren't just slowly coming together, they're also sending out fast jets of gas that are bursting through the cloud around them and making tunnels. These tubes, which are called outflow cavities, aren't just affects. They are important parts of the nebula's jumbled landscape's architecture. These jets clear out space, cut through dust, and change how stars form, just like chisels do in the hands of artists. As a protostar forms inside a dense knot of gas, it begins to pull matter inward through an accretion disk. This swirling disk feeds the young star at its center, but something dramatic happens in the process. Magnetic fields thread through the disk and the forming star, acting like twisted rubber bands. When these fields snap or realign, they launch narrow, focused jets perpendicular to the disk, blasting material out from the poles. These bipolar outflows collide with the surrounding gas at high velocity, heating it and pushing it outward. Over time, the jet doesn't just punch a hole, it hollows out a cone. On either side of the forming star, these cone-shaped outflow cavities expand, forming visible voids in the gas. In Orion, these features are so common and well-defined that astronomers can trace them by their light echoes and shock signatures. What's really strange is how these holes change over time. The star keeps bringing in matter from its disk and shooting out jets, which make the hole bigger and bigger, sometimes up to half a light year across. These aren't just cracks. they're changes to the nebula's structure. They move gas and radiation around and have an effect on where the next generation of stars will form. One of the most famous examples in Orion is the HH-212 protostellar system, captured in exquisite detail by the Atacama Large Millimeter Submillimeter Array, ALMA. It shows perfect bipolar symmetry, like a butterfly in space, with two jets carving deep curving outflow cavities into the surrounding dust. These images are more than just beautiful. They're snapshots of stellar infancy in motion. These holes aren't just empty space, though. Shocks inside them send out waves that heat up areas of gas and leave behind unique chemical fingerprints, such as carbon monoxide, formaldehyde, and even methanol. When the outflow hits the surrounding gas, the sides of the cavities become hotspots of contact that glow in radio and infrared waves. These regions also provide an opportunity to study how stellar feedback scales down. While massive stars shape their environment with intense radiation and stellar winds, smaller stars punch and tunnel their way through the cloud with jets and outflows. It's all part of the same cosmic choreography, just played at different energy levels. Outflow cavities also give us a rare line of sight into the star's hidden interior. Most protostars are wrapped in thick cocoons of dust and gas, making them impossible to see with visible light. But when jets carve out a channel, they create low-density corridors where light can escape. That's why infrared telescopes like Spitzer and JWST are able to peek into these cavities and directly observe the forming star. There are many ways that these holes are a race against time. The more mass a protostar can get rid of, and the easier it is for us to see, the longer it can keep its jet going. It does, however, push some of the gas away that would otherwise fall into the star, which could limit its end mass. It has a built-in way of controlling itself. If there is too much overflow, growth slows down. If there is too little, the star will be buried again. Cavities can also interfere with their neighbors. In a place like Orion, where dozens of young stars form close together, their jets can collide, merge, or sweep across one another's disks. This leads to tangled filaments, twisted Bowshocks, and an entire subclass of glowing knots known as Herbig-Haro objects, bright clumps where jets slam into the interstellar medium at high speed. Dynamical ages. How old are Orion's young stars? In the Orion Nebula, thousands of stars are spread out across gas, dust, and bright threads. It might not be possible to tell who was born when. There are no birth records in space. Starlight beds don't have timestamps. Astronomers have found a way to use both light and motion to turn back the time on stars. As a result, there is an amazingly accurate record of birth, growth, and movement that is etched into Orion itself. This process is called dynamical age estimation. It's the cosmic equivalent of forensic science. Instead of asking how bright a star is or what color it glows, scientists ask, how fast is it moving? In what direction? And what does that say about its past? Let's start with jets. Many of Orion's youngest stars, especially protostars, launch bipolar outflows, narrow jets of material ejected at high speeds. These jets punch through the surrounding gas, leaving visible trails. By measuring the length of the jet and the velocity of the gas within it, astronomers can calculate how long the jet has been active. If a jet is half a light year long and the gas is moving at 200 kilometers per second, then the jet, and by extension the star, must be around a few thousand years old. Another comes from proper motion tracking. Using high-resolution instruments like Hubble or the Very Large Telescope, astronomers can take images of the same stars years apart and detect tiny shifts in their position. Over time, these shifts form motion trails, like footprints frozen in space. By tracing these trails backward, scientists can often identify the region where the star was born and roughly when it left. For example, if a star is currently 0.5 light-years from its birth cluster and moving at 2 kilometers per second, you can estimate that it's been traveling for about 75,000 years. Combine that with other clues like its mass, temperature, and luminosity, and you get a multi-layered age profile. Even the shape of surrounding structures can help. Outflow cavities, shock fronts, and Herbig-Haro objects evolve over time. If we know the speed of the shock and the distance it has traveled, we can derive a dynamical age for the star that launched it. Some of the most iconic Herbig-Haro objects in Orion, like HH34 or HH212, are only a few thousand years old, meaning we're seeing these stars in their cosmic infancy. An important fact comes to light through this kind of detective work. Not all of the stars in Orion are the same age. Not at all. The nebula is home to many generations of stars that formed in waves over the last few million years. Younger protostars are hidden deep in dense gas, while larger stars have moved out into the halo around them. We can start to see a live past of Orion's star-forming engine by making maps of their ages and movements. This history also shows us that star formation in Orion is not random. It's shaped by gravitational collapse, radiation pressure, and feedback from earlier generations of stars. As older stars drift away, they sometimes spark new birth in the surrounding gas, either by compressing it or by leaving behind turbulent voids that destabilize nearby regions. That's why you see clumps of stars at different stages of life, even in close proximity. We can date more than just stars too. The movements of brown dwarfs, Proplids, and even rogue objects with the mass of a planet can be tracked. Some of them look like they were thrown out of the places where they were born by crashes or gravity effects. Their speed and the space between them now can help us figure out when and how that happened. The data points to ejections happening within the last 10,000 years in some cases, which means we're getting these objects in the middle of their flight. All of this information goes into complex simulation models that let scientists play back Orion's development very slowly. These models can figure out the likely order of star formation and gas collapse over time by using present positions, speeds, and gas densities. This gives us a kind of 3D time-lapse account of the nebula. Is the Orion Nebula a star-forming factory or a star-forming fluke? When you get really close to the Orion Nebula, you might think you're seeing the usual way that stars are born: dense clouds, a lot of energy, protostars shooting out, a heavenly stage with both beauty and chaos. When you take a step back, though, a question comes to mind. Is Orion unique? Otherwise, is this the first time we've looked at this example in this way? Astronomers have asked this for decades, because while Orion is the closest massive star-forming region to Earth, it's unclear whether it represents a typical star-forming environment or an unusually active, high-energy outlier. The answer matters, not just for understanding Orion itself, but for understanding how most stars in the universe come into being. When you get really close to the Orion Nebula, you might think you're seeing the usual way that stars are born: dense clouds, a lot of energy, protostars shooting out, a heavenly stage with both beauty and chaos. When you take a step back, though, a question comes to mind. Is Orion unique? Otherwise, is this the first time we've looked at this example in this way? Then there's the presence of rare objects: Proplids, brown dwarfs, planetary mass rogues, all clustered together in a chemically rich, magnetically tangled web. It's a living catalogue of almost every known stage of star formation, from molecular clouds to active jets. Not every region gives us that. And finally, there's the visibility. Because Orion is just 1,300 light-years away, we can study it in detail most other nebulae don't afford. Hubble, Spitzer, ALMA, and JWST have all taken deep looks at Orion, creating one of the best resolved datasets of any nebula in the Milky Way. But when you compare Orion to other galactic nurseries, like the Carina Nebula, NGC 3603, or the Eagle Nebula, certain patterns begin to emerge. Orion is active, yes, but not uniquely so. It falls right in the middle in terms of size, density, and stellar output. There are bigger, more violent places, and there are smaller, quieter ones. If anything, Orion might be typical for star formation in our corner of the galaxy. One thing that stands out, though, is Orion's timing. It is thought that the nebula is less than 3 million years old, which is pretty new. It hasn't been broken up by explosions or spread out by radiation pressure yet. That's just the right amount of activity for it to glow, but not too much for us to study. That lucky time is what lets us see it like in a movie. Another important point is that Orion is not making stars by itself. It is part of a bigger group called the Orion Molecular Cloud, which has other clouds and star-forming areas like L1641, Barnard's Loop, and the Orion B cloud. Together, these areas make up a huge stellar nursery that spans hundreds of light years. This makes it one of the best places to study the whole process of how stars are formed. So what we learn in Orion has echoes across the galaxy. The way stars in Orion cluster, the way jets shape cavities, the way magnetic fields and radiation influence collapse, all of these dynamics are likely at play in other more distant regions. We just don't have the resolution to see them yet. Orion isn't a fluke in this way. It's a model, a case study that puts you in the driver's seat. Astronomers can use it to test their models and make predictions about how stars will behave in systems that are much farther away. Because it's so close, it also helps us understand how we came to be in the universe, since the Sun probably formed in a similar place billions of years ago. That doesn't mean, though, that every area where stars are being born looks like Orion. Because some clouds are not as thick, stars form more slowly. Some of them never make big stars at all. Some are full of metals or magnetic chaos to the point where the process looks very different. Orion might be normal, but it's not the average. The more data we collect, especially with new instruments like the James Webb Space Telescope, the more we'll be able to compare. Already, early JWST observations are uncovering features in distant star-forming galaxies that eerily mirror what we see in Orion. Bipolar jets, dusty Proplids, glowing cavities. It's a strong sign that the physics we've unraveled here may be universal. So, is Orion a place where stars are made, or a one-time cosmic accident? The answer is both. It shows how normal processes work when everything is perfect. A high-quality look at the average of the galaxy. Because of this, it's very useful not just as a nebula, but also as a cosmic model for how stars like our Sun, and maybe even worlds like Earth, form. The hidden population of planetary mass objects. In the shadows, between the bright stars and strands of light that make up the Orion Nebula, there is something strange. Things that are too small to be stars, but float around like they belong in the sky. These are not failed stars or pieces of junk that got away. Asteroid mass objects, or PMOs, are what they are called. And Orion could be hiding hundreds or even thousands of them right out in the open. First, let's define what we're talking about. Planetary mass objects are bodies with masses below 13 Jupiter masses, meaning they're not big enough to sustain nuclear fusion like brown dwarfs do. Yet, unlike planets, they don't orbit a star. They drift alone, glowing faintly in infrared castaways of the cosmic nursery. For decades, the idea of free-floating planets, sometimes called rogue planets, was more science fiction than science. But Orion changed that. As infrared telescopes like Spitzer, Subaru, VLT, and now JWST have sharpened their gaze. They've begun to uncover point sources of light in Orion that shouldn't be there. Too cold, too dim, and too lonely to be stars. One of the first big breakthroughs came in the early 2000s, when surveys detected dozens of objects under the mass of brown dwarfs scattered across Orion. These weren't part of any known stellar systems. They weren't attached to disks or orbiting other bodies. They were just out there. But how do they come together? That's the big puzzle. Two main ideas stand out. First, these PMOs form from gas clumps that collapse, just like stars do. The gas clumps don't have enough mass to start fusion, though. They're like stars that never got big enough. 2. They start out as planets inside protoplanetary disks, but are thrown out furiously by gravity forces or chaotic three-body events. In either case, there will be a world without a father. And Orion, with its chaotic mix of dense clusters, powerful feedback, and constant motion, is the perfect environment for both scenarios. Collapsing cores might fragment into ultra-low mass pieces, and young systems packed with multiple planets might throw one or more out into space before they ever get comfortable. But spotting them isn't easy. These objects are cold and dim, radiating mostly in the mid to far infrared range. You need sensitive instruments and deep exposure times to pick them out from background noise. That's why missions like JWST and ALMA are so crucial. They can peer through dust, capture faint heat signatures, and distinguish PMOs from background galaxies or noise. We are shocked by what we have found so far. Some studies say that for every 100 stars in Orion, there may be 25 to 50 things with the mass of a planet close. That is an amazing number. If it's true, it means that PMOs aren't rare. They're the majority. It's not just numbers either, it's the whole thing. Spectroscopic studies of these objects show that their atmospheres are full of methane, water vapor, and maybe even clouds, just like the atmospheres of gas giants like Jupiter and Saturn. Some of them have rings or streams that look like they might still be taking in matter or even making their own moons. Which begs the question, are these really planets in the traditional sense? Or are they something entirely different? A third class of object, somewhere between planet and star, born alone and destined to wander. Some researchers have proposed renaming them sub-brown dwarfs, free floaters, or even nomads. Whatever you call them, they challenge our definitions. They force us to ask what it means to be a planet. Is it about mass, formation, orbit? If a body forms in isolation but has the mass of Jupiter, is it still a planet or something more? This blurring of categories is part of a broader trend in astronomy. The more we explore regions like Orion, the less rigid our cosmic taxonomies become. Once we thought there were stars and planets, nothing in between. Now we know there's a full gradient, brown dwarfs, rogue planets, hybrid objects, and maybe even dark worlds that formed in ways we haven't imagined yet. Radiative trapping, light caught in the fog. Not all light can get out of the Orion Nebula's bright patterns. Some of it gets caught, absorbed, scattered, and sent out again and again, until it becomes a part of the world it was meant to light up. This process is known as radiation trapping, and it's one of the most important but little understood parts of how stars form. Light doesn't just shine in the middle of Orion, where gas is thick and new stars burn hot. It fights. Consider a new star that is forming deep inside a core of dense clouds. As it gets smaller because of gravity, it starts to heat up and give off radiation, mostly in the form of infrared waves because the thick dust blocks out visible light. However, that energy does not go straight into space. Instead, it hits the dust grains around it, absorbs them, and then sends them back out at a slightly longer range, once more, once more. The light kind of bounces around and gets stuck in the fog of gas and dust that made it. This trapped energy does more than just warm things up. It changes the thermodynamic structure of the cloud. In regions where radiative trapping is strong, heat builds up and prevents further gravitational collapse. This can halt the formation of nearby stars, or at least delay it, by increasing thermal pressure and stabilizing the gas. Instead of winds or jets, a star in the process of birth might stop the birth of its friends with light. For example, in Orion, hundreds of stars are growing very close together, so this is very important. The densest clumps, which have the most chance of making new stars, are often surrounded by dusty, opaque cocoons. Light from nearby protostars gets stuck in these clumps and adds energy that slows the fall of the gas. This energy stops the formation of stars. Simulations of radiative feedback in regions like Orion have shown that without radiative trapping, clouds would collapse more rapidly and produce a far greater number of low-mass stars. With trapping in play, the stellar mass function shifts, and fewer stars form overall, but the ones that do form may have more time to grow massive. This could partly explain why the Trapezium Cluster is so dominated by high-mass stars. There's also a spectral side to this. Radiative trapping shifts the energy of the region, transforming what would otherwise be short wavelength radiation into longer infrared signals. This is why instruments like the James Webb Space Telescope and ALMA are game changers. They allow us to see the thermal footprints of trapped radiation, subtle temperature gradients, glow signatures, and even movement within the fog. In some parts of Orion, like the BNKL region, radiative trapping is at its most extreme. There, the gas is so thick and the embedded source is so hot that light can't escape for tens of thousands of years. What we see from Earth is only the faintest infrared whisper of what's actually happening inside. Some of the most energetic processes, like massive protostars fusing deuterium or launching massive outflows, are completely hidden behind this veil. On the other hand, that veil is what keeps everything together. Radiative trapping controls temperature, keeps gas from collapsing, and decides how fast stars are born. It's the unseen builder working through the light that young stars give off that shapes the nursery. There's even a feedback loop. As stars grow and emit more radiation, they increase trapping, which changes the collapse pattern, which changes the environment for future stars. It's a dynamic, self-modulating system, and one that's extremely difficult to model, yet absolutely critical to understand. Radiative trapping also ties directly into the initial mass function, IMF, the statistical distribution of star masses in a given region. In Orion, the IMF seems slightly top-heavy, meaning more massive stars are forming than expected. Trapping may be one of the reasons. By inhibiting low mass collapse and allowing select cores to feed longer, light literally sculpts the stellar hierarchy. Orion's tails, streamers and evaporating globules. If you look closely enough at the Orion Nebula, past the bright clouds and stars, you'll see dim trails. These are wisps of gas that look like comets traveling behind tight knots. There is no visible noise or extra thought here. They are called evaporating gaseous globules, EGs, and they are one of the most dangerous and delicate parts of the process of stars growing. If you think of these as tails, streamers, and globules, they are where the pull of gravity and the push of radiation meet. At their core, these structures are small, dense pockets of gas, tiny compared to the larger nebula, but massive enough to potentially birth stars or substellar objects. The problem? They're sitting in the path of a stellar hurricane. Intense ultraviolet radiation from stars like Theta 1 Orionis C slams into these dense clumps, heating the outer layers and causing gas to boil off. Over time, this gas gets stripped away in long, trailing tails, creating the streamer-like appearance we observe in high-resolution imagery. This process is called photoevaporation, and it's one of the most aggressive forms of environmental feedback in a nebula. A globule that might have otherwise collapsed into a brown dwarf, or even a planet-forming disk, gets shredded by radiation before it ever has the chance. In Orion, this phenomenon is rampant, especially near the central Trapezium Cluster, where radiation levels are extreme. But photoevaporation doesn't always kill a star in the womb. Sometimes, it's just enough pressure to accelerate collapse inside the clump. Radiation compresses the globule from the outside, pushing gas inward while also stripping it away from the surface. This balance can ignite a fast-track route to star formation, triggered by destruction, sculpted by erosion. Hubble images of Orion have famously captured these globules with bright heads and trailing tails, like tadpoles in space. Many are oriented in the same direction, pointing away from the trapezium, a visual signature of the immense radiation flooding through the region. The tails are often many times longer than the heads, glowing faintly in ionized hydrogen or sulfur light, as if marking the escape routes of heated particles. These buildings will not last forever. Indeed, they are short-lived and weak, lasting only a few thousand years at most before disappearing or changing into something else. That makes Orion a very rare way to see how stars change at this point in their lives. Most places where stars are being formed are either too far away to see in this level of detail, or don't have enough energy to make stars. It's also interesting to see how many different kinds of things these tails can hold. Some globules don't have any stars at all, they just have dark groups that are vanishing. Others hide protostars that can only be seen in infrared light. Some of them even have planetary mass objects or brown dwarfs inside them, which suggests that not all stars are formed by big, sudden crashes. Some are formed slowly, under attack. On a broader scale, these streamers help map out the radiation field of the entire nebula. By studying their orientation, length, and erosion rate, astronomers can back-calculate the UV intensity and direction from nearby stars. It's like seeing wind by watching the way grass bends, but on a cosmic scale. And in Orion, the wind never stops blowing. Recent JWST images are now beginning to resolve these globules with unprecedented clarity, revealing internal structures, spirals, knots, jets, that suggest active formation inside these eroding cocoons. In some cases, the radiation may actually be helping to clear away excess material, allowing light from the embedded protostar to finally escape. The very force that threatens their survival also becomes the stagehand for their grand reveal. Radiation, gravity, and the harsh climate of Orion have shaped these streamers and globules into statues. They show how people have survived and broken down in the face of destruction. They also tell us that beauty can still appear in the midst of chaos. Stellar nurseries within the nursery, clumps inside clumps. The Orion Nebula looks like a single cloud at first glance. It looks like a big bright tube where stars are born. But when you zoom in, the image falls apart. What looks like it's uniform isn't. The galaxy is broken up, twisted, and organized in a hierarchy. Instead of one big nursery, there are many smaller ones that work together to make a web. Each group of nurseries looks like a star on its own clock. In Orion, stars are born inside of other stars. This makes it one of the most complicated places in the sky for making stars. Astronomers call this phenomenon hierarchical fragmentation, and it's a game changer. Rather than the gas cloud collapsing as one big unit, it fractures into smaller clumps, then subclumps, and then again, each governed by its own temperature, density, and magnetic conditions. Imagine a Russian nesting doll, but each layer is an active stellar womb. These clumps inside clumps aren't theoretical. We see them clearly in submillimeter and radio observations, especially from instruments like ALMA and VLA. Deep within Orion's filaments and cores lie compact regions, some only a few hundred astronomical units across, where gravity is in the final stages of collapsing material into protostars. Each of these may eventually birth one or more stars, all while remaining embedded in a larger collapsing cloud. This nested structure creates multiple generations of star formation, sometimes in the same place. A massive star might already be lighting up the nebula, sending out UV radiation and shock waves. While just a few light days away, a dense clump is still shielding a low-mass protostar from detection. The result? A nebula filled with infant, toddler, and adolescent stars, all coexisting in the same chaotic cosmic nursery. What's even more interesting is how isolated some of these little groups can be. While star winds and photoionization make the Trapezium Cluster roar, some outer strands of Orion have deeply embedded cores that don't seem to be affected by the violence going on around them. These cold, dark areas can only be seen in radio or far infrared wavelengths. They are protected by layers of dust that keep heat in and let the fall happen quietly and without any problems. This variation creates stellar diversity. Stars born deep within protected clumps may have longer accretion phases, resulting in more massive disks and potentially larger planets. Others, forming closer to radiation sources, may have their disks eroded early, limiting their potential planetary systems. In effect, the nebula becomes a testbed for every possible star formation scenario all at once. And it's not just about mass. Chemical composition varies too. Some clumps are rich in complex organic molecules, including PA8s, methanol, and ammonia, while others are more pristine. This influences everything from the cooling rate of the gas to the formation of prebiotic molecules, a hint at how planetary systems might inherit wildly different starting conditions. But perhaps the most radical idea tied to hierarchical fragmentation is this: some of these smaller clumps may never fully collapse. Instead, they drift, cool, and break apart again, creating even smaller structures. It's possible that the planetary mass objects we see in Orion as discussed earlier, originated in clumps that fragmented at the lowest possible mass scale, never crossing the threshold to become full-fledged stars or brown dwarfs. This goes against the long-held belief that planets form in rings and stars form from clouds. Orion gives us a more fluid picture of what happens. A gradient of collapse, where conditions, time, and the surroundings all work together to shape what comes out. The process isn't neat, it's bad, complex, and keeps making copies of itself. Still, order comes from chaos. It's likely that hierarchical star formation is the main way that stars are born in our galaxy. There is a lot of proof that stars are not born alone, but in layers. This is true for both nearby clouds like Orion and faraway starbursts in other galaxies. Inside bubbles, in groups inside groups. Could Orion go supernova? The future of the trapezium stars. 4 huge stars shine brighter than almost everything else in the area at the center of the Orion Nebula. These giants, which are part of the Trapezium Cluster, are young, hot, and very unstable. They live quickly and use up their nuclear fuel without thinking twice. They are all very big, but Theta 1 Orionis C is the biggest and strongest. And like all big stars, its end will not be slow death, but furious explosion. What this means is we need to know if Orion could go supernova. It's not just yes, it's a question of when. Big stars don't last very long. The Sun lives for 10 billion years, which is a very long time. But a star like Theta 1 Orionis C is racing to the finish line in just a few million years. It is already an O-type star, and its ultraviolet rays are strong enough to cut holes in the cloud around it and give off the ionization glow that we see from Earth. On the inside, though, it's going through fast core fusion, which is changing hydrogen into helium, and then stronger elements in a chain reaction that ends with an iron core. Once it reaches that point, the game is over. Iron fusion consumes energy rather than releasing it, and when the pressure of fusion no longer supports the star's massive weight, the core collapses. In less than a second, the outer layers rebound off the imploding core and explode outward in a cataclysmic supernova. For the Orion Nebula, the consequences would be dramatic. A supernova from Theta 1 Orionis C, or any of the massive stars nearby, would release enough energy to disrupt the gas and dust across a large portion of the nebula. Shock waves would ripple outward at thousands of kilometers per second, compressing nearby gas clouds while shredding others. Any still-forming stars or planetary disks in the vicinity would be blasted or evaporated, ending their development instantly. But this is also how the cycle of making things keeps going. It is known that supernova shock waves can cause stars to form by pushing down on gas in nearby areas. It's possible that parts of Orion that haven't collapsed yet could be set on fire by the deaths of nearby stars. In this way, the death of one generation sets the stage for the rise of another, which is a sad but beautiful extension of the nebula's purpose. We already have signs that this process may have happened before. The massive Orion Eridanus superbubble, a vast shell of hot gas encompassing the Orion molecular cloud, is believed to have been carved by multiple past supernovae, possibly from earlier stellar generations now gone. In that context, the next explosion in Orion wouldn't be an outlier. It would be part of a rhythm, a heartbeat. The potential danger to Earth from such an event is minimal. At roughly 1,300 light-years away, even a supernova of enormous energy would only result in a modest increase in cosmic rays reaching our planet. But for astronomers, it would be the event of the century. Supernovae within our galaxy are rare, and one this close would allow unprecedented observation of stellar death, chemical enrichment, and nebula reprocessing in real time. Some models even suggest that Orion could host multiple supernovae in the coming few million years. Several other massive stars in the region, both within the trapezium and in neighboring subgroups like Orion OB1, are ticking time bombs. If more than one were to go off within a relatively short cosmic interval, the entire Orion complex could transform into a supernova remnant, like the Veil Nebula or Cassiopeia A. The gas in the Orion Nebula may have been spread out, the dust may have been heated up, and the stars may have died or been separated. But new things will grow from the ashes of that destruction. Thicker areas full of heavy elements that can form hard planets, moons, and maybe even life. The Orion Nebula isn't just a beautiful part of the sky. It's also a live laboratory where stars are born, changed, and then killed over the course of millions of years. From the glowing gas and secret planets to the fear of supernovae, Orion holds the answers to how we got here in the universe. If this journey lit a fire of curiosity in you, subscribe to Beyond Horizons, where we explore the universe's most mind-bending mysteries, one nebula at a time.